Welcome. Thank you. Welcome everybody to the latest edition of the Global Network on Sustainability in Space workshop / Sandpit program. For the next few hours, we're going to hopefully do a bit of a deeper dive into some of the information that was discussed in our workshop, which was held back in July, if I remember correctly. So quite a bit of a blur with so many events going on through GNOSIS. And at that workshop, we explored some concepts and ideas for novel and non-traditional space surveillance techniques. The idea of these discussions is hopefully to generate some finance and funding opportunities for universities to be able to do some deeper research. And over the next couple of hours, we're going to have the pleasure of 2 universities to help guide us through some different options. And after this event, we will then hopefully have the opportunity to discuss and delve into some potential funding streams. So over the next few hours, you're not going to have to listen to me too much, so you'll be happy to know about that. In a few minutes' time, I'll be able to introduce you to Shawn Goldsborough, the UK Space Agency Senior Orbital Analyst. I thought, thanks to our Russian colleagues of a month or so ago of adding a few objects into orbit for us to deal with, I thought it'd be great to actually invite somebody who's at the sharp end of space surveillance and tracking, actually applying all that data that we hope to gather for them to be able to ensure we get a much better space picture, an understanding about space sustainability, compliance, and more importantly, I suppose, protect and defend any assets on orbit and to help ensure the long-term sustainability. So Shawn will be speaking for up to half an hour on the trials and tribulations of dealing with the aftermath of the event and hopefully open some interesting points and questions on how difficult it is at actually putting this data use into practice, or even getting hold of the data in any great depth. After he's spoken, Max and his team from Strathclyde will introduce us to some radar concepts, and then later, after a break, James and his team from Durham will talk to more about the optical piece. And I know that Max's team has got some additions to add on hyperspectral tracking capabilities. Stuart Eves at the AAM later on will then introduce us to an update on what's been happening with the GNOSIS challenges, which were introduced during the conference back in September. And then I will finish the event by just providing a brief overview of what we've discussed, and then handing over some thoughts about how we can potentially take this forward and if there are some funding streams available. 1700 is the planned end. More than happy if you want to chat on beyond there, and we remain as flexible as possible. The whole idea of this is some concepts are being introduced by our good friends and colleagues from Strathclyde and Durham, but these are discussion topics, so please participate as much as possible. So I shall now hand over to either Max or Carmen if they're here. Sorry, I'm got ahead of myself there. Hand over to Shawn, and hopefully we'll be able to hand the picture over so that he can do his presentation on the Russian ASAT. You with us, Shawn?
Yeah, no worries. Yeah, thanks, Dins. I'll just try and share the screen just a moment. Everybody see that?
We can, yes. I shall stop my video and mute.
Thanks. Okay, thanks, Dins. Yeah, so good afternoon, everyone. So I know many of you already, but my name's Shawn Goldsborough. I'm UK Space Agency Senior Orbital Analyst. As Dins already said, he asked me to come along and give you a brief presentation about some of the challenges that we deal with fragmentation events like the Russian ASAT that we've recently seen. In the interest of time, I'm going to keep this reasonably short, but if there's a bit of time for questions at the end, and if there's anything I can't answer today, I'll come back later and get back to you. Okay, so I'm going to talk briefly about a few things. I'm going to talk about the fragmentation event goals. What is it that we actually look to achieve when something like this happens? I'm going to take you through a very high level, I have to stress, but operational timeline of what we did specifically for the Cosmos 1408 event, the challenges that we have in events like this, some impacts, long-term impacts, and evolution of SST at the Space Agency and UK Spock. So just to start with, when there's a fragmentation event like this, and I am going to keep this focused on operations, which is where I think a lot of the relevance comes in. We have two primary near-term operational goals, requirements that we look at. The first one is we need to understand the event as thoroughly as possible and in as timely manner as possible as well. That includes things such as the base object, knowing what that is. Unlike the recent Russian event, for us, we weren't working at the sensor level when this first occurred. Sensor operators themselves are going to see events like this unfold in front of them without any prior knowledge. If you've got a surveillance sensor where most of these things are picked up, you'll start to see debris come through your field of view that you didn't expect. And there's quite a bit of work, as you would imagine, that goes into identifying in the first instance what the object was, what was the source of this new debris. Another element that we need to understand very quickly is what are the number of fragments look like? How many fragments have been created from this event? What are the orbital characteristics of those fragments? Where are they? What's the trajectory look like? When do we think the event occurred? And what do we think the possible cause is, which is obviously very difficult in many circumstances. We also need to understand what the impact on our satellites of interest are. Whoever you are performing this task, you will have, I imagine, satellites of interest, of particular interest, a prioritization list. What's the near-term and long-term risk to those? So I'll take you through quickly the operational timeline of how we reacted to the Russian ASAT event. Again, if there's any questions on this, I can come back to those at the end. So first of all, this particular event occurred at 0247 on the 15th. Yes, on the 15th of November. We were alerted to it not too long after that, and work really commenced around 7:30 in the morning. So in the UK Space Operations Centre, between ourselves and MOD colleagues, we started looking at this. Now, in the first instance, when something happens of this nature, it's very difficult to acquire any meaningful data quickly, but we still have a requirement to understand what's actually unfolding and what the implications of this actually are. So in the first instance, we actually run a simulation of the event with the information that we have. We need some base understanding of that. We need to understand what we believe the object was. We have to have a rough approximation of mass of any objects involved. And we do need to ideally have a time. You can work with that in other ways, but ultimately we simulate what the breakup fragmentation event would look like to get a rough understanding, and it is rough, of a worst case or a most likely worst case picture of the event. In this particular case, the simulations that we ran gave us a result of around 1,579 pieces of debris. Now, this is over 10 centimeters. I'll come back to this later, but we don't simulate anything smaller than that, and that in itself is an issue we deal with both in the simulation side and in the data that we actually, the observation data that we actually acquire. At the time when anything like this happens, we always go out and task sensors that are available to us. So we have a list of civil sensors we have available to us, and also some sensors available to us via the UK Spock. So straight away, our initial reaction is to try and understand as best as we can with the limited information that we have, what the fallout of an event like this could look like. From there, we take those the simulated debris that we now have, and we have to put that through some kind of risk assessment to understand what that means for objects that we care about. Now, in our day-to-day role, those objects, as you would imagine, for the UK Space Agency, are UK objects of interest, UK licensed objects. And on the UK Spock generally, obviously there are some military assets that we care about too. When we take that data, again, stressing that this is very rough approximate data, we simulate the debris and we create a rough orbital plane for the objects. We take that data and we then put that through a first stage conjunction screening process where we literally just propagate the orbits and look to tag those up with objects of interest to see what comes within 2 kilometers and 10 kilometers of the objects that we care about. That doesn't provide us with conjunction assessment at any real detailed level. All it does is enable us to understand in the first instance a rough approximation of increased risk to the objects that we care about at the altitudes where the debris sits. We then also perform that process again, but for the whole catalog. We do that to understand some of the questions we have about the wider environment, and also we have other partners that we work with just that we assist in these times. Clearly, we also have an interest in manned spaceflight, so the ISS especially is something that we look at there. Now, there's quite a gap here, because the next time we get anything meaningful that we can really dig our teeth into is actually up to 5 to 6 days later in this case. Now, this time frame changes. It changes depending on the event, who we're working with, the sensors available to us. Lots of different elements come into this, variables that can affect how long it takes for us to start to get meaningful, real data through that's actually usable for true analysis. In this particular case, it was around 6 days before we started to get anything meaningful from the USSSN, which is what I'm displaying to you on this slide. We initially received around 280 fragments. This was sent as analyst element sets to us. We put that again through some of the risk assessment tools and algorithms that we've got, as I mentioned before, that we used for the simulated data, and looked again at increased risk. On the right, you can see a Gabbard plot of that diagram showing the altitudes of the debris. And on the conjunction screening that we did, even just with these 280 fragments, approximately 280 fragments, there was a 10% increase in average collision risk that we calculated. That was within 10-kilometer thresholds. The number of tracked fragments increased very quickly, actually. It says gradually, but quite quickly over the next day or two, to around 350, and then went up to 400 not about a week later. After that, we started to compare the data that we'd received to what we'd simulated. We do this whenever there's an event like this to validate what we said in the first instance, in some regard at least, look at whether it's comparable and what we expected. We do that in any event like this. We'd obtained data at this point from UK civil sensors as well. I'll talk about those a little bit later, and that's commercial and government. And we also received some data from RFI windows, and all of this was incorporated into some post-event analysis that we were doing to validate what we'd seen and to rerun risk assessments and conjunction assessments. When we actually received the data we were waiting for, some real true data, which to be honest didn't take 6 days in the first instance. It was just 6 days until we received something we could really use for more intensive risk assessment purposes. We had received something before then, which at least enabled us to confirm to some degree that the event probably happened around the time that we were informed in the first instance by doing pinch point analysis, which is something you can do to identify where an event probably occurred due to minimum separation of the fragments at the time. Currently, as of yesterday, there are around 800 fragments in the catalogue and analyst element sets available to us. 300 of those, sorry, are actually in the public catalogue. That debris, you can see that graphed on the right in the Gabbard plot and also in the SMA altitude graph. This event, like any other event of this magnitude, will actually continue to be dealt with for a long time from an operational perspective of identifying objects, cataloging new objects, and ensuring that the data that we have on them is as good as possible for understanding where they are at any time and feeding those into conjunction screening processes. These things can take a very long time, as I'm sure you're all aware. We will continue to monitor this, as it says there, of course, throughout. This is a video I just want to show quickly. The purpose of this video, it was actually, in case you haven't seen it before, it was provided on a blog that the UK Space Agency did. But there's something in this video particularly that I just want to focus on for the purpose of this discussion, which is the debris itself. So clearly the ISS is not to scale, which is in the video. That was a request from those above us who wanted to see something to do with manned spaceflight in there for a particular reason. What I want to focus on with this is just the debris, and actually the spread of the debris. So when the event first occurs, and this is the same with any event like this, you can see that the debris is very congested. There's very little separation between debris objects there, and that spreads out reasonably over a few hours, but it remains extremely difficult to observe, identify single objects within that cluster of debris and build good orbits on. And I'll come back to that shortly. But ultimately, the problem that we have from a SST perspective, what can we do with sensors to understand what we're seeing? One of the major issues that we have revolves around the fact that this debris is very congested. It's very close together, very difficult to resolve multiple objects in the early phases of an event like this. That causes us all kinds of issues. Another problem that we have is that the debris spreads in ways that we can't necessarily predict. So in our simulations, we can absolutely simulate changes in altitude, quite dramatic changes in altitude and orbital trajectory. But when we actually start to receive observed data, observations of actual objects, you do tend to find that those particular objects are missing in a lot of cases. You don't see those because by the time the sensors have been tasked and they've been looking at where they believe the debris is, and then they start to look wider, that debris is very hard to identify again and locate. This video, it's worth mentioning, is actually based on simulated data, not observation data. And again, the reason I wanted to show this was just to focus on the spread of debris in the early phases of an event like this. And when I can figure out to get to the next slide, there we go. So I think this is where we start to get to some areas which are really of interest, which is what our challenges are. It's all well and good saying what we've done, but there's a lot of challenges that we face when we're looking at an event like this that need to be considered. The first one, as I've just talked to there, is observing the debris. In the early phases of an event like this, I've already said, resolving multiple objects that are very close together is incredibly difficult. That the debris is so close together that it's a challenge, and that's one of the major reasons why we don't see real data for a reasonable period of time post-event. Because of that fact, and the fact that when you do get observation data on an object, it's often either cross-tagged, or even if it isn't, the number of observations that are available at any one time are very low. It's incredibly difficult to perform an OD of any kind, orbit determination of any kind, to calculate a good orbit on those objects. And that results in very difficult tasking processes, because you need to understand what to task the next sensor on. And if you don't have a good orbit for the objects, essentially you're just redoing the same thing. You're capturing new objects again and trying to run an IOD. And it remains very difficult, for quite a while. You'll find this is why you usually get 10, 50, 100 objects coming through a week, maybe later after the event, because those are the objects that start to genuinely spread away from the cluster of debris. Eventually, this will increase in volume of data that we receive as the debris spreads. Because of these things, the TLE data that we receive as well, which is the calculated orbits and the state vectors from that, are very substandard in quality. They're very poor, and the only thing they're really valuable for is just confirming an understanding of altitude spreads and things like that. It's not something we would ever consider putting into something like a conjunction process. We wouldn't use TLEs in a conjunction process anyway, but in this particular case, I mean, that goes without saying, it's just not worth the effort. You can use them for very rough understandings, as we did, of risk assessment, but it comes with a huge pinch of salt. Another challenge that we have, as I've already alluded to, is lost debris. So you do get objects with dramatic shift in orbital trajectory when the event occurs from something like an ASAT, especially, of course. So there's a lot of debris there that is actually large enough to track that we still don't see for either a long time and sometimes months, or even objects that crop up. I've seen objects crop up years afterwards that have then been catalogued as something that they believe was an event that, I mean, I'm not sure how accurately you can even do that, but I know that that's occurred before. High latency is an issue. So calculating reasonable orbits, as I've said, is incredibly difficult in the early phases. Promoting them to the actual public catalogue on the US side takes a long time generally. Again, we are now a month later, and there's 300 objects catalogued out of what we believe is a possible 1,500 that's been seen-ish. And I've not even spoken yet about the bottom bullet point here, which is small debris objects. So time is an issue. General lack of available data, as I say, I'm repeating this again, but is a problem. We had a big gap between the first day that we were looking at this and essentially 6 days later when it comes to reasonable volumes of at least at best, average quality data. That's an issue. We're in the dark, for want of a better term, for quite a while. And then finally, small object tracking is a huge problem, as I'm sure you're all very much aware. We typically say we can only track down to about 10 centimeters size with current technology. That's true, give or take a centimeter here or there. Generally, As you know, with an event like this, there can be thousands upon thousands, hundreds of thousands potentially of objects smaller than 10 centimeters that we can't see. Those are the objects that we're most concerned about because we have no idea where they are. So this is a huge challenge that we've got. There's a large volume of the population is currently unknown. So developing an understanding of a fragmentation event and calculating risk, that has to be something that we still aim to achieve, even though we've got these challenges. It's incredibly difficult. Long-term impacts of this, at the operational level of what we do day to day, we're constantly looking at what is the increase risk to UK satellites when there's been an event of this nature. That changes over time because new objects are identified, orbit data becomes more accurate. I'm not going to say it's extremely accurate, but more accurate than it would have been in the first instance, so we can keep rerunning and understanding risk. That goes also for key partners objects and manned spaceflight as well. And we also need to constantly reassess our actual resource and computational capabilities to perform these tasks too. As the debris population grows and general satellite catalog population grows, we need to be able to handle those levels of data and the tasks that come with that. At international forums, I've only mentioned one, which is one that I'm involved in for the UK Space Agency, so I can comment on what we've done, which is the Interagency Debris Committee, the IDC. And the working group I'm involved in, Working Group 1, where we deal with measurements, we've started a collaborative observation campaign working with different nations to bring our data together to try and understand what the long-term implications on the environment are. There will be work going on at other forums, but I won't comment on those directly right now. There's another point to make on the long-term impacts here. This will have an impact for some time on the operational process and the ConOps of a number of operators, including OneWeb and Starlink, with SpaceX with Starlink, where they operate in some way around these altitudes. So that's now increased risk to them. And also to the ISS, of course, it's increased risk to the ISS as well. So UK space surveillance and tracking, again, with an operational focus, is evolving all the time. We at the UK Space Agency, working with the UK mod constantly, we've been working with the UK SPOC for a while to try and work with them, improve the capabilities there, and really bring that forward together. That's for orbital analysis, sensor operations, their protect and defend mission, and other focuses as well. We're always trying to further and improve the relationship that we have with the US. We worked with them very closely for a long time, primarily through the military routes. But from the civil routes in the UK Space Agency, we're really starting to build a good relationship there directly as well, but a collaborative one as well with ourselves in the UK MOD. And that enables us to acquire data that we wouldn't necessarily get otherwise and share outputs with them. Commercial sensor providers were recently contracted by the UK Space Agency. This was put out in the public domain, so I'm sure you're all aware. Numerica were brought in to do deep space tracking for us, and Leolabs and the NOS Loki system brought in for low Earth orbit tracking. So as they begin to ramp up with us and we finalize ingestion of all the possible data sets they can provide to us, that'll increase our capabilities quite dramatically in these areas, actually. I haven't mentioned there, but I should have done, that there are also some government civil sensors that we utilize. NERC provide us with an optical telescope, Jeff, and at Chilbolton as well, STFC provide us with Castor, which is a 25-meter LEO radar dish, and also COATS, which is an optical system. So we do have other sensors too. We're currently working on a pilot project with UK satellite operators called Monitor My Satellites, which is a program which enables us to provide them directly with conjunction analysis services. So that's something that we started looking at. That kicks off in January in a pilot phase for 12 months. And that involves us internally deriving risk to them, conjunction analysis outputs, probabilities, missed distances, etc. And also we've just started a requirement study where we'll be looking at reevaluating requirements for the UK SST and operational needs. So there's a lot of things ongoing. There's a lot more than that, but that's just the operationally focused areas. And that's everything. I've breezed through that a little bit, so if you've got any questions, please ask. And again, if I can't answer anything now for any reason, I can always come back to you later. So thank you.
If I could ask everybody to use the raise hands function if you do have any questions, I shall introduce them individually to Shawn. Any questions for the floor? Stuart, I think you should go first.
Thanks very much, Diz. Shawn, the list that you put up of things that you are seeking to discover about an event didn't include the sort of geographic location over which the event has taken place, but I wondered whether that is relevant in this case. The video that you showed seemed to imply that the actual conjunction and fragmentation event was somewhere over the Pacific Ocean, but I would have assumed perhaps that it occurred over Russia. Is that true?
Yeah, I think the video is slightly misleading because of the fact that we had to focus on the ISS for the requirements of the video in the first instance. So yeah, we believe, as I think is sort of public knowledge, that this was, you know, a Russian ASAT event, in which case it would have happened somewhere over Russia. Well,
I was assuming that was the case in the sense that that seemed the likely trajectory, but there are some implications, I think, of that fact. One is that, if you're trying to test the hypothesis, was it a Russian ASAT? If it was over Russia at the time, then that supports the hypothesis. And if the fragmentation appears to have occurred somewhere else, then perhaps it doesn't support the hypothesis. But the other implication, I think, is that irrespective of whether the Russians were watching with their sensors to see what they'd achieved with their ASAT test, it's almost inevitable that there's going to be some sort of time lag between the fragmentation and event and our opportunity to see it, because it's over Russia and we don't have access to sensors that can actually observe the location where the initial event happens. So, there's almost inevitably a time lag in the data that we're going to get. Things will spread apart before we get to see them. Is that also true?
Yeah, absolutely. Yeah, that's absolutely true. Yes. Yeah, gaps in that time frame will. Yeah, we absolutely have to deal with that accordingly. I mean, we won't see that event clearly until it comes through one of our sensors, and that isn't going to be over Russia. So yeah, there's an absolute latency there that we have to be aware of.
Cheers, mate. Thank you.
Yeah, no problem. Thanks.
And Will Finline, you had a question?
Hey, Shawn, thanks for a really interesting presentation. I think it was on your second or third slide, you talked about modeling the breakup, and I was just wondering what tools you use to do that. Yeah,
no worries. That's a good question. So essentially, and we've done some evaluation of these of the tools that we use and the equations that we use in this. There are some issues with the quality at some level, but not to the point where it's a major problem for what we do with it. So we use the NASA breakup model at the foundational level, and then we essentially we wrote our own tools on top of that to take the outputs of that, create TLEs, and propagate those and model what they look like. So at the absolute base level, it's essentially the NASA breakup model that we utilize. And again, we've done some fairly deep assessments on that to understand what the limitations of that are, what it's useful for, what it isn't useful for, because it absolutely isn't perfect, but none of the models that we've looked at are. So it's, as long as we understand what the problems are with the model, we can deal with that accordingly, which I'm confident we do. So it could be better, but it's acceptable at the moment in its current form.
Thanks very much.
Yeah, no worries. Thanks, Will. And I think Duncan's got his hand up, Dins, if that's okay.
Yeah, sorry, I couldn't unmute my mic to say, Duncan, your question, but thanks for getting that, Shawn. Duncan, over to you.
Hi, thank you, Shawn. I was wondering, just following your response to the last question, and forgive me, you may have addressed part of this earlier in the presentation. Do you have a view on whether there are still objects to be found, or is, in this particular case, is there a significant difference between the number of tracked objects and the number you might expect to see from the NASA breakup model?
Yeah, again, that's another good question. Yeah, I think it depends on how we define found. And well, actually, it probably doesn't depend that much, because I think the answer is yes either way. That there are a number of objects that we don't have data for that I can use through the processes that I've outlined yet, that we've actually observed, but can't build even remotely good enough orbits on yet to actually do something with that data. So it definitely won't be catalogued, and it's not even got, this data isn't even available as analyst element sets. So the number of objects that have been observed is higher than the numbers that I reference in the presentation in general, but I can't confirm the exact number, but it is higher, and it's more in line with what we would expect to see. But I absolutely...
Somehow you got muted there, Shawn.
Oh, how strange! Not sure that happened. What was the last thing you heard me say?
I've been trying to do that for years. Damn. Yeah, you were just talking about the figures, basically.
Yeah, I'll start again. Sorry about that, Duncan. I don't know what happened there. Yeah, essentially what I was saying was, yes, I think there will be more objects observed and catalogued in the future. The time it takes to do that will vary depending on the objects that we're trying to observe and catalogue. But the numbers that are presented in the presentation include debris that have been added into the satellite catalogue and analyst element sets. But there are also objects that we've observed that we just can't build orbits on quite yet because the data is so poor on top of those. So I believe that the number of debris objects will be much closer to what the simulation said by the time that we've done. But what that time frame will be, I have no idea. And of course, as I said earlier, we're only talking now about objects that we can actually observe. There are many, many more objects smaller than, we say 10 centimeters, but than what we can observe with current technology in a routine manner to catalogue. So I can only guesstimate how many objects there are that are much smaller than that.
Thank you. In fact, the origin of my question was heading towards, I'd seen an opinion posted by Darren McKnight of Leo Labs, and I don't know if this is still his current view, but he was suggesting that the smaller number of observed fragments actually was meaningful in terms of the likely collision velocities, in that the ASAT interceptor hit its target from so that their combined velocity was actually somewhat less than orbital velocity. I don't know if it's just something, let's say, open quotes, just something I read, close quotes, but because it came from Darren McKnight, I thought there might be something to it, but that was it. Thank you. Yeah,
no problem. I mean, all I'll say on that is that it's not unfeasible that you can do some correlation there to understand the situation with the velocities.
Okay, thank you.
Yeah, I'd also like to point out the fact that it takes the 18th some time to put all the objects into the catalogue as well, because of the processes they have to go through. If anybody remembers back to the Iridium Cosmos collision, it actually occurred a month before I took over as OC Ops at RAF Fylingdales in 2009, and they didn't finish getting all those objects into the catalogue until January 2012, about 3 months before I left Fylingdales, because they've got to be, without doubt, they've got to be able to apportion it to that event so that they can put it in the catalogue. And Chris Dawn, I won't steal any of your time. You have a question for Shawn.
Thank you. It was following up really on what Shawn was just saying, and indeed what Duncan was just talking about in terms of the fragmentation sort of characteristics. You know, when I was looking at this, I realised that we've got quite a few objects that had gone quite a long way out of the original orbit, and that tended to suggest to me that it had been hit with something fairly large, fairly directly, rather than some sort of fragmentation warhead from a standoff distance, which would just sort of rip through it and rip the thing apart. So when Shawn was sort of talking about the problems with the NASA fragmentation model and so on, and the assumptions that go into that, probably the key thing I think for all of us in look at these things is there's a huge amount of uncertainty in what hit it, and therefore how it's broken up, and therefore where all the bits are going at what speed.
Yeah, absolutely, Chris. I agree with that completely. One of the challenges we've got with simulating these in the first place is the NASA breakup model isn't really designed for something like this. You can use it for collisions, catastrophic understanding of a collision on orbit, but it doesn't lend itself well to an ASAT event. So you have to deal with that accordingly in the way that you assess the outputs and understand the inputs that you're giving it. It definitely decreases the value of the model when you deal with an ASAT versus a potential collision or an explosion on orbit of a rocket, say.
There was a lot of work done a few years ago that was reported open source in terms of some of the ballistic missile defense studies, where people were trying to design really smart warheads that detected which side of the object they were, and therefore, you know, triggered their initiation in different ways to create different impact clouds. So there's lots of things like that that could have possibly been drawn across into an ASAT system.
Yeah, absolutely. Thanks, Chris.
So is there, I was going to say, anybody with a hand up, but James, it looks like you have a question as well.
Yeah, thanks, Dins. It was going back to something you said actually of how long it takes to essentially, you know, match up a piece of debris to an event, and therefore how long it takes to put into the catalogue. Is it sort of more of an administrative problem there, or is it a case that you're trying to make sure that you're not duplicating something that's already in the catalogue? Because if it's the former, is it not more sensible to have it put in the catalogue as, say, you know, pending, if you know what I mean, and know that there's an object there before you can assign it to say, this is a piece of debris from this particular collision? I just wonder what the sort of barriers are in the way of that.
Yeah, so that's a good question as well. So the cataloging process is not that straightforward as you would imagine. So with anything, in the first stages, when the US, this is obviously the US side I'm referring to, the catalog that we all use publicly, when something like this occurs, the first stage is to obviously understand the orbits as best as you can. And while that process is going on, anything that they can build an orbit on that is remotely useful, they will put into the analyst catalog, which is a back-end catalog that not everybody will see all the data from, but they have internally and will share what they can accordingly. When they have an orbit on those objects that they are reasonably confident with, they can, and sometimes do, promote those to the catalogue, but don't, as you essentially alluded to there, actually fill out all the areas of the SATCAT to state this was a part of this event or this launch. They will sometimes just put something in the catalogue to get it in there with a number, call it object A or something, and then give the information, the absolute bare minimum information. But generally, they do wait until they can reference things like an international designator or a launch date with something before they catalogue it. So it's kind of at their discretion, I guess, to a degree, but there is a process they have for how they promote things into the catalogue gradually. The difficulty with something like this is if they're not going to put something into catalogue until they are confident enough to associate it with an object or a launch, which would then obviously correlate that with the ASAT event, then it will stay as an analyst object for some time, most likely, because it's not something that they usually do. So it's a legacy process that I have, but seems to have worked for them to date, in their opinion. So I don't see that changing anytime soon, but I'm assuming that.
Thanks for that, Shawn.
Yeah, no problem.
And Stuart, you have another question?
It's not a question, it's a comment in response to James's question. About a decade ago, I had the opportunity to meet one of the people from the 18th at a Shriva war game, and we had a conversation about the cataloguing of the debris objects from the Chinese ASAT test. And one of the things that the member of the US Air Force said to me at the time was, when I commented that, you know, as you pointed out, Dins, the process was taking a long time to actually get the stuff into the catalogue. Her point to me was, well, Stuart, there are only 3 of us that are actually authorised to put stuff into the catalogue, having done the attribution process that you were alluding to. So there is, I think, a sort of pragmatic issue about the number of people that the US had for doing this sort of stuff back then. Whether the situation has changed, I don't know.
Yeah, I probably can't comment specifically on numbers of people promoting things, but I know that the process is being evolved fairly regularly with regard at the moment with regards to how they handle some of these things due to the large increase in objects in large constellations coming, things like that. I think probably having a couple of people only putting things up to the catalogue is not quite acceptable where it used to be. But I can't comment on whether they've actually implemented those changes or not. It's just, it would surprise me very much if they're still at that level, but they could be. It does take time to do, so it's not impossible.
Yeah.
Shawn, thank you very much for that great presentation. I thought it'd be a great idea for you to be able to talk about the, for want of a better phrase, the pains of actually doing the practical job, whilst we speculate on how best we can get more data on objects for you, to you, and whatever else like that. And it's an interesting point that actually we've sort of like finished on talking about the trials and tribulations about being able to get that information into the catalogue. You know, if you think about it, it takes time for them to attribute the objects to an event. It takes time for the UN to get the registration information into their registry, et cetera. So it's there's always a lot of speed bumps when we have objects that are orbiting the Earth at faster than a speeding bullet. So it's interesting times. So on behalf of everybody, Shawn, I'd like to thank you very much for that. Please do stay and listen as much as you can. I know you're a very, very busy man, and I can give you plenty of feedback at a later date anyway. Thank you for that.
Yeah, no problem. Thanks for the opportunity. I'll stick around as long as I can. Thank you.
Okay, so now I'm going to hand over to University of Strathclyde, who are going to take over hopefully the screen sharing and take us on a route for the next hour to talk about various projects they've been doing to do with radar, and for us to scope some ideas for further research on supporting space surveillance data through radar capabilities. Carmen, are you there?
Yes, hi. Yes, hi. Good afternoon, everyone. My name is Carmine Clemente, and I am a reader at the University of Strathclyde, and I am the director of the Sensor Signal Processing and Security Labs. And for a number of years now, I've been working also with Max Basile from the Mechanical Aerospace Department at our university on a number of activities related to SST or SSA, in particular using novel radar sensors. So I was asked to chair this session, and I'm just going to give you a brief introduction to the problem of the radar sensing from a system point of view. What are the potential systems that are available? And then we will have a couple of presentations, 3 presentations actually, on some activities that we are doing at Strathclyde. And then we will have basically an open forum to discuss about some of the questions that I have, but for anything that you might that might come to your mind that you might want to discuss related to this field. So let's start talking about radar sensors for SST or SSA, whatever you want to call it. So why do you want to use radars? Well, basically radars can offer a number of benefits to detect, track, and perhaps also image through the synthetic aperture or inverse synthetic aperture techniques of the space objects. Their advantages in terms of the capability to operate in any weather and light conditions. They can cover actually wide areas, especially large radars with electronically steering arrays, and they can have multifunctions, so they can be able to work with multiple functions, so from detection to actually change to tracking a specific space object if needed. And then there are additional capabilities that can be integrated, like diversities in the spatial domain, in the frequency domain, or in polarization domain. That are things that are not yet been explored for this specific challenge. What is the main limitation? The main limitation is basically the power that the radar system needs to transmit, or we can translate it in signal to noise ratio that we receive on the receiver, or from practical terms, what is the minimum detectable size that of the target that we can detect and track, perhaps. So this is something that needs to be taken into consideration when designing a system, and different systems can provide different characteristics, different advantages, and can be used for different purposes, or can be integrated with other systems differently. So if we look back in time at what is available and what are traditional radar systems used for SST, they've generally been using historically lower frequencies to deal with the attenuation, basically due to the R to the power 4 denominator in the radar equation, basically. And they were using a narrow bandwidth, so we were not getting nice spatial resolution. With the advent of commercial and also with the higher requirements for defense and security for SST, more complex radar systems have been developed. And it is very beneficial because there are many more players in the field, a lot of more data, more interesting solutions, radar using higher frequencies, higher powers, larger bandwidths capable to provide the final resolutions, and also using electronically steered array. But most of the operational radars are still have something that is common to them, that they are monostatic radars. So the simpler type of radar by the definition, they are bulky, big, heavy, expensive systems. So from a research perspective, at least, and also for potential commercial venues, there is the need to try to identify what alternative solutions, what alternative radar systems could provide technical advantages and also operational advantages. So I want to do this exercise of try to classify different types of radars. So the radars can be classified according to several planes, if you want. So here I want to start to do this classification in terms of if we have the radar or mainly the receiver based on the ground or at sea, basically on the Earth, or if we want to have the receiver in space, which is another alternative solution that could be used and that is still less mature as a technology. So for ground-based radar, we can have an active radar, which is basically a radar that transmits its own signal and receives its own signal, and can be monostatic, which is traditional radar transmitting and receiving in the same location. And as I say, this type of technology, while it is quite robust and well established, it's not been fully explored for this challenge. There are several aspects of this technology that monostatic radar that can still be investigated. For example, can we push higher in frequency, meaning that we need to have higher power transmitters? And I think there is some interesting work being done at St. Andrews with the physics department at Strathclyde currently. I think it was presented at the last Sandpit in this area. Polarimetry. So radar polarimetric information carries interesting insight. This is not something that is currently investigated in this domain. What can be done to investigate? Is the cost really the barrier, or is there something that can really bring operational advantage? So this is probably more a research question, but something that has not been investigated yet. Other advanced concepts like holographic and MIMO are also things that are still open. Bistatic, I don't know why it's happening this. So bistatic is also a type of active radar where basically you have a receiver that is not co-located with the transmitter. And whether we have a cooperative transmitter, we can think that we might have a cheaper version of the bistatic where we have that receiver is an existing facility or existing receiver, for example, a radio telescope used to reused for the SST purpose. Or multistatic, so where we can actually extend this concept further, where we have multiple receivers and where we can exploit spatial diversity for basically the ability to see the target from different aspect angles and thus improve the target state vectors estimation. Again, we can also have a different concept of radar, not only active, but passive. A passive radar is a radar that does not own the source of illumination. So basically, the transmitter is an illuminator of opportunity. Typical are communication systems like DVB-T, DVB-S, and so on. So we can think about a passive radar, ground-based receiver using illuminator opportunity, and this is be static by definition because you have just to place a receiver. This has advantages that it is a cheaper system compared to an active system because it does not require to have its own transmitter. So you can probably have a multitude of them for a fraction of the cost. And this can provide advantages, but basically, given the fact that you have a fraction of the cost, you can scale it up to a multi-static receivers. This is a quite advanced concept, and it's quite complex to realize because you need to have synchronization between the receivers. You must have a good knowledge about the position and the waveform transmitted by the transmitter. What you can do is that you perhaps can investigate the different solutions, and you can observe a multitude of potential illuminators, not only ground-based, let's say an uplink station used as illuminator, but you can also look, so for example, a geostationary DVB-S satellite used for as illuminator opportunity. The advantage that these systems could provide is exploiting the larger bandwidth or the frequencies that are usually allocated for communications to observe targets. On the other side, we can also consider the case in which we have the radar or the radar receiver only on board a spaceborne platform. So this would give you the advantage that you have something that is closer to space debris. So this would imply that you have to transmit less power to reach the space debris, or at parity of power, you can be able to see smaller targets. So where do we put the radar? Well, depending on the configuration, you may want to put it above or below the space debris ring, basically. That depends on the specific configuration and specific design of radar to have. And also in this case, we might have an active radar system on board of a satellite that can be basically looking from the bottom up or from top down, depending on what you prefer to do. Generally speaking, it's probably better to have it looking from the bottom up to reduce the noise from the Earth. And again, this can be monostatic, which is probably the simple things to do. And I think there is some interesting work done at the University of Birmingham in this area, investigating sub-terahertz radars for SST on board of satellites. And this system has the potential to detect smaller targets, because of the fact that they are closer, or that can have be using a very high frequency and basically leading to very fine spatial resolution, supporting the actual recognition, identification of the target. Multistatic, bistatic in this scenario is not very practical because it's very, very complex domain. So I've not suggested it here, but we can have passive. So you will see also in some presentation later that you can think to have a passive radar receiver on board of a satellite, meaning that you do not have to have high power requirements because you do not need to transmit anything, but you can think to receive signals that are reflected by the space debris when either the signal is transmitted from a satellite, can be a commercial communication satellite, or if the signal is transmitted from the Earth up and then backscattered or forward scattered towards the satellites. So you can have a space-based illuminator of opportunity, as I said, another satellite, a MEO or a GEO illuminator of opportunity that is doing its job, and you are just exploiting its RF energy backscattered or forward scattered by the target, or a ground-based one where you basically apply the same principle. You're only using a ground-based illuminator. In both cases, backscattering or forward scattering configuration can be investigated, and they have both cases they have low power requirements. So all these systems have the potential to bring benefits to the SST community, and I think that some of these were suggested also in July's workshop. A couple will be suggested today, but mainly the message is that some of these are investigated at various levels of TRL. Some companies are proposing to actually develop some of this type of systems. Some are still under investigation at academic level. So there's things going on in this area, but there are definitely more things to be investigated, and definitely the challenges. There are many challenges at various levels because once you have identified the system, then you have to do the processing and the algorithms that will be bespoke and peculiar to specific systems. Some of these systems perhaps may not be yet investigated or are at lower TRL. And what I would like to do after the presentations today is to basically investigate with you all which of the approaches that we have seen, or something else that might come to your mind that I haven't thought about, has the higher potential to provide the higher impact, both technically, operationally, and commercially to the SST community. What is easier to develop and validate? So probably a passive rather than an active on the ground is probably easier than one in space, perhaps. What requires more fundamental level development? So what is something that is still worth staying in academia or in RTOs? And what are the new technologies that might come in the next few years that could enable and facilitate the life of these more advanced systems? So said so, I'm happy to take any quick questions. Otherwise, I will move to straight into the talks from our speakers, and then we will have the open discussion. So is there any question? If not, we have the first speaker here, Christos Siliodis. Christos is a research fellow and Royal Academy of Engineering Intelligent Community fellow at the Science of Signal Processing and Security Labs. So Christos, the audience is yours.
Well, thank you very much for the kind introduction, Carmen, and thank you all for having me today. So today I'm going to give you a short presentation of, let me try to put it in full screen. So can everybody see this? Just a yes on.
Yes, thanks. Yeah.
Looks good to me.
Okay, perfect. Thank you very much. So yes, so today I'm going to give you a short presentation on a new concept for space situation awareness called Intercontinental Radar Bistatic System, or IRSI, or IRIS in short. Before going into the actual presentation, I would like to say that this is a DASA-funded project. It hasn't been started yet, so I'm not going to show any results, but just introduce the idea in order to, let's say, spark a discussion later on. Okay. So I had introduction slides for space situation awareness, but I think this is something that everyone here is familiar with. Of course, we know why it's very important. We have this ever-increasing number of space missions, and we know what is the potential catastrophic effect of a collision. So one collision can lead to more collision, and this cascade effect can actually make future space missions even harder. Another topic that I would like to touch is that monitoring targets such as ballistic missiles and spy satellites make space situation awareness very, very critical for national defense. So not only commercial application, but also very, very important for defense applications. So moving into the radar part, I know Carmen made a nice introduction of radars, and I will like to talk here a bit more for those who are not specialists. So in space situation awareness, the primary use of radar is this monostatic configuration that Carmen described. So we have one transmitter pointing its antenna into the space, transmitting a signal, then switching its antenna to the receiver mode in order to be able to get the reflections of the target. Another way that you can use radar is to actually employ some local radio telescopes in order to receive this signal. So those telescopes do not actually transmit anything, they just act as passive receivers, so that they listen all the time. We transmit a signal from the radar, we receive on the radar, but we can also receive on those radio telescopes. Of course, they have to be compatible, they have to be working the same frequency, and so on. The reason why we do that is because those radio telescopes are much more sensitive in most cases than what the receiver that we're going to have on the radar, and therefore we can have a little bit better performance. For example, I have here the TIRA. I think it's tracking and imaging radar located in Fraunhofer in Germany, and if it's used on its own, it will have a detection threshold of a size of 2 centimeters. This is for 1,000 kilometers. So the typical size of the target, the typical dimension, we can say, has to be at least 2 centimeters in order to be able to detect it, or it can be larger. And now when we actually use this in a combination with the Effelsberg, I hope I pronounced it correctly, telescope. I have telescopes there, it's typo. A telescope which is around 20 kilometers farther away from the location of the radar, we can bring this detection threshold down to 1 centimeter. And this, I guess, again, because of the sensitivity that we have on the radio telescope. The good thing is that the radio telescope is already there. We don't need to let's say, apply the cost for putting new hardware. Of course, we have to rent the time and allocate these resources, but still, it's a nice way to reuse existing facilities. Now, one might say that this is a kind of bistatic configuration, and this is the way that I have it here in the slides, because the transmitter and the receiver are not located in the same place. In fact, it's 20 kilometers, quite far away. But if we put everything into perspective, the relative distance from the target is so high that we can assume that this is a pseudo-monostatic configuration. So here you can see how everything will look like into perspective. So if we see the Earth from the space, I'm just using Google Earth here, but we can see how relatively small this distance is, imagining that a target is in orbit. So that's why we would expect this system to perform very close to what we'll have from a monostatic radar system. Of course, there are some synchronization that we have to resolve, but the main radar processing will be very close to what we'll have on a monostatic. Now moving to the new concept that I would like to speak today, the long baseline bistatic radar. So a few years ago, or should I say 1 or 2 years ago, the NATO set 293, called RF Sensing and Space Situation Awareness, actually started investigating and testing this concept. So instead of having a radio receiver, radio telescope collocated in a broad manner, or be, let's say, local to the space radar, now we want to have it much farther away. That's why the long baseline term comes to. And this can help us, let's say this will lead to a combination of monostatic radar, so the transmission reflection from the same position, and this distributed bistatic pairs. So for this, I have here an example, a graph. So we have a monostatic radar located here, and this can be even a pseudo monostatic. So we have a radar and a radio telescope in close proximity. We transmit the signal, we can see with a red color, and we receive the reflection from the target, as we can see from the green. So while this is happening, we can have other passive receivers, so other radio frequency telescopes located in different parts of the globe. And of course, depending on the configuration that we have, so where the target is positioned to and where the transmitter is, we should be able to receive these these radar signal reflections. So of course, we don't expect to be able to see it if we're on the other side of the globe, but these configurations could actually be implemented using real world radar and RF telescopes. So that's why there's a testing here as well. So there have been held some tests. I'm not going to share any information, but this is a technology that is applicable, let's say. Now, the reason why we're interested in this kind of configurations, because we can have multiple observations of the target using just a single transmission. So we have this observation, and we may be able also to have this radio telescope close to us. So we can say that we have two observations, but in reality, we see the target from the same point of view. So the range that we're going to detect, the angular location of the target, even the velocity that we can extract, for example, from Doppler, would be more or less the same, because if you put it in perspective, we see the target exactly from the same location. However, we have these telescopes located at different points. We're going to observe the target from a different point of view. So you have this bistatic angle from here to here that is much larger than 0 degrees than what we have here. So why, again, this is important is because compared to pseudo-monostatic observations or monostatic observations, a distributed network can capture simultaneously these multiple position, velocity, and even radar cross-section observations of the target. Now, when I'm saying radar cross-section, this actually has to simply put it with the reflectivity of the target when observed from a particular aspect angle. So if we observe the targets, if the signal transmitted and the observer is exactly is placed exactly the same location, we can see we can get one value. So, for example, for the RCS, while if this bistatic angle decreases, we'll be able to get different kind of reflections, and in some cases this can be higher than the monostatic. So we can have this kind of advantages. Now the problem is that by having more sensors, this system will require more complex signal processing frameworks. We'll have some synchronization issues probably, and these are some problems that we'll have to solve. So more information, we need also to find a way to process and combine all this data. So AIM of this project, of this upcoming project, is to develop a complete model and processing framework of such a system and assess its performance. So actually prove that this can be beneficial and can perform significantly better than just having one transmitter receiver pair. Now I'm getting very close to the end of the presentation, and what I would like to include is some connection with some existing work that we have held. So multi-static and MIMO, multiple input, multiple output radar configurations have already demonstrated their advantages. So this is an extreme case because we have a target into space, so the ranges are much larger, and we have this different kind of sensor. So each telescope might give us a different, let's say, format of data, might have different sampling rates, for example. But theoretically and even in practice, we have seen that having these distributed systems actually can have some advantages. First of all, here I have an example of how by the bistatic RCS, so this measure of reflectivity, lightly put it, of the targets can be significantly higher compared to the monostatic. So in this example, we have a wave, an electromagnetic wave induced from this direction. I hope you can see my cursor. And this is what would be the RCS if, or the received power, if we see, if we placed the receiver at different points. So we can see that we can get, even at this direction, significantly higher radar cross-section area. That means that the SNR will be higher, which is something that we always strive for. Another thing that we have seen in the past is that we can do Doppler or micro Doppler. This refers to, let's say, micro motions, not just the main motion of the target. That by doing this kind of analysis using distributed configuration, we can improve classification of motion. So the test that we did was with human targets, but the same principle can apply to any kind of target if we have this motion. So here you can see an example of how these configurations look like. So we have this collocated configuration where the transmitter and the receiver are in the same place, more or less. And this is the distributed configuration, closer to what we're proposing here, where we observe the target from different point of views. Finally, there is some work that we have been done in MIMO, ambiguity function. So ambiguity function in the radar is sort of a metric of how you're expecting the system to perform based on the waveform that you use, but in MIMO systems, also based on the configuration of the sensors, so the placements of the sensors that you're going to have. And this can help us as an evaluation and assessment tool of how the system will perform, and we can also use it as a design tool. So you can imagine if we would like to place a new space situation awareness radar, we can use such a tool in order to place it at the best position to be able to collaborate better with the other RF telescopes that are available. We have also done some work, and I haven't included here, my bad, with MIMO ambiguity function in a similar but different concept. So we used it in order to detect drones. So in that case, we have multiple transmitters. We use GNSS satellites, and we have one receiver. So we use the multiple transmitters. In that case, we'll have one transmitter and multiple receivers in order to be able to detect the target. And we saw that by combining all these different bistatic pairs, we're able to improve the detection performance. So that's all from me, and I'm happy to take any questions.
Good, thanks, Christos. I think it's better if we keep the questions for the end of the presentations.
Sure.
So I will move to next presentation. Is from Sebastian Diaz Rio Frio. Sebastian is a PhD student working with myself and Max Vasile on a project funded by the European Space Agency, and is going to give us an insight on this project.
Hi, good evening to all of you. Thank you very much for having me. My name is Sebastian Diaz, and I'm a PhD student at the University of Strathclyde, and I'm going to talk to you a little bit about my project, which is a space and ground-based radars for detection of the space debris. So, first of all, a little bit of the motivation behind my PhD is that during the last years, there has been an increasing number of space objects orbiting around Earth. So that has led to an increased possibility of these objects colliding with each other. And to minimize the collision risk, there is a need for detecting and tracking these objects. More concretely, even though that Europe has great and good capabilities for the detection of the space objects, these are quite limited. For example, the FGNA tracking and imaging radar, even though it has high capabilities, it is also high power, consumes lots of power, and it is high cost of maintenance and also the proper the construction of the FGNA itself. Another reason for my project is that many of the antennas utilized for the tracking and imaging of the space debris are primarily used for radio astronomy, which itself isn't a problem, but using or having a radar focused only antenna would be would be much more practical. So first of all, I would like to talk to you about the the space segment of my project, the spaceborne passive radar for space debris imaging. Feasibility study was done on this new space-based passive radar system for space situational awareness. And this system was compromised by an illuminator of opportunity and a CubeSat at a lower altitude. And this CubeSat will be deployed with a software-defined radio and a passive antenna to perform the task for space surveillance. This radar system would have the forward scatter configuration, meaning that the bistatic angle, the angle between the illuminator and the CubeSat, which is the receiver, would be around 180 degrees. So meaning that it would be a passive radar. For performing the radar tasks, the CSR imaging shadow inverse synthetic aperture radar algorithms will be employed. It must be said that for these algorithms, the position and the velocity of the object must be estimated. And at the end of the whole process, a figure we would end up with the complex profile function of the target, which is the figure on the right. So one of the main problems with this system is that many times the power of the illuminator of opportunity is not high enough so that the SNR at the end of the CubeSat segment is high enough so that the target can be detected. For this reason, I designed a multiple observation integration approach for CSR imaging radar, which would be basically, we would have the illuminator of opportunity on one side, the CubeSat on the other side, using the forward scatter configuration. The target would be crossing, and we would be using 3 channels, or any amount of channels, but in this case would be 3. This channel will be set at different frequencies, and basically with each channel we would have 1 observation, and at the end of the process, at the end of the CSR imaging algorithm, we would have 3 observations of the same targets. With these observations, we could perform non-coherent or coherent averaging. In the non-coherent averaging, the complex profile function is integrated in a non-coherent way, meaning that only the magnitude of the complex profile function is used. And in the coherent way, in the coherent averaging, the whole complex profile function would be used. Some preliminary results. On the left, we have the ideal complex profile function, the complex profile function with no noise. On the right, we have the complex profile function with no averaging, with only one channel, and a signal to noise ratio of minus 25 decibels. And we can see that even though the complex profile function is somehow similar to the original complex profile function, it would not be detectable. So by using 3 channels, which means that we are using 3 observations, in the case of the non-coherent averaging, the one on the left, we can see that the complex profile function assimilates to the original target quite nicely. And on the right, we have the complex profile function with coherent averaging, and once again, 3 observations. That fits better the targets. Next, I'm going to present you the ground-based multiple pulse repetition frequency radar. The characteristics of this ground-based radar is that it would be an active radar and ideally would cover from horizon to horizon. For this purpose, I'm using a novel 3D phased array antenna, which in principle would cover all the azimuths and all the elevations. One of the problems of using such a large cover space with the radar is that there would be many Doppler and range ambiguities. And to solve these Doppler and range ambiguities, I would be using a multiple pulse repetition frequency. And since I cannot, well, since the coherence through the whole process cannot be ensured, I'm using a pseudo-coherent integration approach for integrating all the pulses that might come from the targets. So so I'm going to show you next the minimum detectable size for this method. Well, first, sorry, I forgot to tell you that by using this multiple pulse repetition frequencies, I would be covering 3 sections of the space. The first one would use the 3 pulse repetition frequencies. The second one would only be using 2, and the third one would only just be using 1 of them. So the minimum with this approach, the minimum detectable size would go from around 24 or 39 centimeters to 4 or 7 meters, all by using 3 different bandwidths. In the first case, when using the 3 different pulse repetition frequencies. In the second case, when only using the 2 pulse repetition frequencies, we would cover from 600 to 800 kilometers, and the minimum detectable size would go from around 7 meters to 40 meters. And in the last case, when using only one of the pulse repetition frequencies, when going from 800 to 10,000 kilometers, the minimum detectable size would increase dramatically and would go from 50 meters to up to even 200 meters. So the future work involving my project would, in the case of the space-based radar, would involve some forward scattering signal reconstruction techniques, the use of a classifier for the non-coherent and the coherent averaging cases, and in the case of the ground-based radar, since all the returns from the targets might have different ranges, I should be using or I should investigate the use of the different range compensation techniques. And since for the last case, the one when using only one pulse repetition frequency, the minimum detectable size are quite large, I should investigate on using new parameters to reduce this detectable size. Thank you very much, and I will answer any possible questions that you might have.
Okay, thank you, Sebastian. So we leave the questions for later on.
All right.
So the next talk is from Prof. Massimiliano Vasile. So I think that most of you already know Max, but if not, I think I'm sure he will introduce himself. So Max, the audience is yours.
Okay, thank you very much, Carmine, and good afternoon, everyone. My name is Max Vasile. I hope you can see my presentation. So as Carmine said, we have been working together for quite some time on different techniques for SST based on radars. And the idea is to integrate these techniques into a framework that we are developing. It's called Cassandra. Cassandra is a artificial intelligence agent that is connecting and collecting different tools that we are developing in order to improve space traffic management and multiple different aspects of space traffic management, in fact. So Cassandra was originally funded by ESA, and it's still funded by ESA. It received contribution from the European Commission, and now we have also some funding from the UK Space Agency, specifically to integrate the work that I'm doing with Carmine within this framework. So I wanted to give you an overview of the framework, just to let you understand exactly what we are doing and how the radar is connected to the rest of the modules inside this artificial intelligence agent. So the idea of Cassandra, which stands for Computational Agent for Space Situational Awareness and Debris Remediation Automation, is to improve the way we manage the environment around the Earth by creating a pipeline of different tools and introducing in this pipeline some intelligence to make informed decisions. So within Cassandra, we have a tracking part that is, for example, the work that Carmine has been doing on radars, that connects to a module that analyzes conjunctions and then makes decision on possible collision avoidance maneuvers. And within this module, we have our propagators and our analysis of uncertainty. And then there is another set of modules that instead are more related to what happens if objects are re-entering, and they are modeling and simulating the demise process and the future of the fragments if they hit the ground or if they disperse in the atmosphere. So this is a general portrait of all the modules that are contained in Cassandra. So the top left, you see the radar bit that connects to what we call the multiple cause encounter analysis tool, which analyzes the catalog in general and detects possible conjunction events that require further attention. And we have two modules that are more connected to the improvement of the modeling of the dynamics of the objects from measurements. One is very much focused on the modeling of the atmospheric drag, and the other one is instead detecting possible anomalies in the dynamics of the object. Then we have three modules that are connected together. One is the core of the intelligence of Cassandra that is analyzing possible conjunctions and making decisions on whether those conjunctions can lead to a collision. And as a response to that, there can be further observations to acquire additional information, or there can be the allocation of a collision avoidance maneuver. And then we have two modules that instead are taking over if the trajectory of the object is intersecting the atmosphere, and are looking at the re-entry phase, at the fragmentation in the atmosphere, and the demise of the object. So the radar is at the moment in a phase of integration with the rest of the modules. Basically, what we are doing is to take the two talk that you heard before and deriving from the information that the radar can give us a preliminary orbit determination for an object, and then propagate the orbit with the uncertainty associated to the orbit through our propagator up to the point of expected close encounter, and there we can calculate the probability of collision. So I'm not going to describe too much about the other modules apart from this one, because it's quite interesting, because once we have information about the orbit and the associated uncertainty, we have different techniques to quickly analyze possible existing future conjunctions. At the moment, we are working on an horizon of about a week. And then from this screening of the possible conjunctions, we extract a short list of conjunctions that need to be analyzed further. And these conjunctions, go to the intelligent classification system. As I said before, this is where a lot of the intelligence of Cassandra is. And there we use a very interesting technique, because we are not just calculating or making decision on the pure probability of collision. We are looking at the probability of collision and at the confidence that we have on the correctness of the probability of collision. And this confidence can come from different elements. One could be the source of the data. Another one could be the type of conjunction event. Or we can ingest CDMs, for example. And if CDMs are provided in a time series, we can build a distribution model, a probabilistic model on the CDMs themselves, and derive from that an estimation of the credibility of the calculation of the probability of collision. Now, the ICS has been trained on tens of thousands of possible scenarios with possible conjunction event and reaction to that. And basically, every time there is a new conjunction, the ICS can provide a possible decision in response to that scenario very fast, without the need of repropagating orbits or recalculating anything. And one output could be the allocation on new measurements, new observations, if there is enough time, or the generation of an optimal collision avoidance maneuver. If there is the need of further observation, the ICS calls this module, which is our state estimation module, that perform propagation, uncertainty propagation along the orbit, and calculate, again, the probability of collision and the confidence on the probability of collision. And if instead there is the need to implement a collision avoidance maneuver, the module calculates a robust optimal collision avoidance maneuver. It is robust in the sense that it accounts for the uncertainty on the probability of a collision, and it's optimal in the sense that it tries to find the minimum propellant required to execute the maneuver. And this module implements both impulsive maneuvers and low thrust maneuvers for the maneuverable spacecraft. As I said, the other two modules are more dedicated to re-entry, so I'm not going to discuss much about that. What is happening now in the latest project that we have supported by the UK Space Agency is the integration of the radar part with these three modules, so the classifier, the state estimation, and the collision avoidance maneuver module. This is a typical pipeline that Cassandra could handle. So we have observation coming in. We discriminate if there is a conjunction event that requires further analysis. Then we estimate the probability of collision and the confidence in that. The ICS provides a decision, a robust decision, because that accounts for the uncertainty on the estimation. Then if there is a low risk of a possible collision, then nothing is done. If there is a risk, but there is too much uncertainty on the probability of collision, then the ICS allocates further observation and calls the module with the radar to allocate observations. Otherwise, it allocates a collision avoidance maneuver. So as I said, the classifier has a very smart way of dealing with different events depending on the amount of information that is available and on the confidence in the information, on the measurement. We define 5 classes of possible actions that the operator can take. The first 2 imply the execution of a collision avoidance maneuver because there's no opportunity to acquire new measurements. Class 3 instead is no collision avoidance maneuver, but requires some measurements. And class 4 and 5 is no collision avoidance maneuver is required. And in some cases, even no observation is required because the probability is very low and there's enough information to be confident in the fact that there is not going to be a collision. This is an example of some of the outputs that we tested on real cases of conjunctions, assuming that we can have measurements at different times. For example, in this case, the first set of measurements was at 48 hours from close encounter. Then we performed a state estimation, and this gave us a confidence interval on the probability of collision that you see here at the bottom between 0 and 2 to the -4. So the probability of collision could be inside that range, but clearly there's not enough information there to make a decision. So we need to locate a further observation that is taken at 24 hours before the expected close encounter. And that gives us a different estimation. In fact, the upper probability of and this means that we are expected to perform a collision avoidance maneuver. So in this case, we allocate a maneuver that effectively reduces the probability of collision down to 10 to the -8. So these are some references. So happy to provide publications if you want to know more. And this is the end of my presentation.
Okay, thank you, Max. Okay, so now we have some time for some Q&A, and I'll be happy to take Q&A on our presentations, and then we can move quickly towards maybe an open discussion if we have time. I don't know. The organizers can tell me. So, is there any question for us? Said, yes.
Hello. Well, actually, I have a very general question about that. I mean, I'm just wondering what range and sizes are you hoping to achieve by developing these new radar systems? Because I mean, there are a few different talks, and I've seen different ranges and capabilities from different people presenting. But I'm wondering, each of them, what would be the kind of a target for the range and sizes of the objects they think they can catalog? And I mean, I don't know, for detection. And I'm not sure about the accuracy of the detection and how it can be used for the cataloging system. But if they can.
Yes, well, the actual size, as I said in my presentation, that depends on the actual signal-to-noise ratio that you get on the receiver. So basically, this depends how much power you can get on the target and how far you are from the target. So from cases where, for example, you have an active radar on board on a satellite that could be in maybe a couple of hundreds of kilometers or less, even 50 kilometers from the target, you can aim at centimeter size target probably. I think it's the work that the colleagues in Birmingham have been doing with the sub-terahertz radar. They've really been looking at very small targets because they were firing a reasonable amount of power from the satellite. So it really depends on what is the minimum thing that you might want to be interested with, and how big is your sensor. You know, from the ground you might have a large antenna, and you can integrate multiple signals with a distributed system, for example. And in that case, you can try to push down the minimum size. And the exercise that the project that Christos presented as that as objective. So quantify what is the minimum detectable size that you could detect with a system like that one, where you have multiple receivers on the ground exploiting the same source of illumination. The accuracy is also another exercise that we are looking at currently with the project that Max mentioned at UKS, funded by the UKSA, where based on the accuracy that we can have from the radar sensors, from the measurement model, because we have a certain resolution in range and in azimuth and elevation angle, but the target can be wherever in that resolution cell. So that can be a first uncertainty that we might have. But then you have also uncertainty on the position of the platform where the radar is, as well as the uncertainty on the attitude of the radar. And these are all things that we are taking into account and that we are investigating currently. I hope that this answers your question.
And just quickly, what would be for example, what would be the kind of range and size you're hoping? That's what I'm kind of mainly interested. I mean, based on the current information you have, what do you think would be the kind of maximum so far?
Well, that depends on the system that you develop. So you can design a system, for example, a passive radar on a satellite, and you can put a larger antenna, and then you can try to aim for a smaller size. It's all a trade-off that you can get. What we are doing, we are investigating concepts, and then of course, if you want to put on a 10 EU satellite, you have more space to put a larger antenna, and you can aim to detect smaller targets and look at longer ranges. If you are looking at if you have a smaller satellite that you want to use, you can use a smaller antenna. It means that you have less capabilities. So this all depends on a trade-off on the design that you have and that you want to deploy. Even for the ground-based, you've seen as an example, you've seen the ranges and sizes that Sebastian presented. Those were for a radar with a very low power transmitted. We are now updating those results with a more realistic radar, so with a few kilowatts of power, and we're aiming to look at centimeter size targets that we would expect to have as a result.
Great, thank you.
Stuart?
It was actually a comment for Max on his chain of different pieces of software. When you get to the point of doing a conjunction avoidance maneuver, obviously, if you're a solitary satellite in space, then potentially you may just do a single collision avoidance maneuver. But obviously, if you're part of a constellation, there is perhaps a requirement to occupy a particular slot within that constellation. So it may not just be a case of maneuvering out of the way of a piece of debris. You may have to maneuver back into your slot afterwards in order to maintain the configuration of the constellation. Now, I think there are some circumstances where you may be able to achieve that sort of by advancing or possibly even retarding a planned station keeping maneuver that you were going to do anyway. But if the former scenario applies and you do have to make multiple maneuvers, I think it's possible that operators might have different criteria that they would be applying. So those criteria could include minimizing the amount of fuel that you use, minimizing the amount of time you spend outside your slot. It might include saying something like, well, I've got a fixed amount of fuel that I'm prepared to use for this maneuver, but I'd like to maneuver in a direction and at a time that would maximize my separation from the object that's coming towards me to minimize my risk of a collision. So it seems to me that there is quite a sort of sophisticated decision tree that you might have to go through at some point with a number of different parameters that you might be trying to optimize, and it could be some combination of the things that I've mentioned. So whilst I'm delighted that you're making the progress that you are, I think there may be sort of further modules that we might want to add to your tree in the future.
Well, okay, so let me maybe explain this, because maybe you understood that it was optimal only with respect to fuel. So the actual optimization of the maneuver contains also a number of constraints. So the decision is not made only on the basis of the optimality with respect to propellant, for example. So what you said about maneuvering in a direction that maximizes your life, that is included in the robust optimization, because in the moment in which you calculate a maneuver accounting for the uncertainty on the probability of collision, you maneuver in the direction that allows you the maximum separation, if you want, and that leads to a minimization of the risk. Okay. So that is already included. Then there are other criteria that we use that derive from operational constraints that I didn't explain, but are part of the decision of which maneuver to implement. And often those constraints are more related to when to perform the maneuver rather than the direction of the maneuver. And in terms of going back to the original orbit, that is is part of the module, but is not, I'm going to say, is not that important with respect to the others, because the difficult part is to make a decision of when and which maneuver to perform. So that's why I explained that part. Of course, if you are in a constellation, there are other logics that dictate how to go back to your operational conditions. And those are part of the criteria, the constraints that we inserted also in the decision making. But it doesn't require another module. It's already there.
Okay.
Okay, good. Do we have any further question? Okay, so according to the agenda, now there should be the break. I don't know, Deans, should we go ahead with a short discussion if there is any anybody that's willing to discuss further my questions, or should we just take a break now?
I would say maybe a mixture of two if people should wish. We certainly won't start the next session until on the half hour. And if in the meantime you want to actually discuss whilst taking a break, then that'd be good. Otherwise, we'll just have a for want of a better phrase, a bathroom break for everybody. I need to recharge my coffee mug.
Okay, yes. So I was introducing this question basically. So what are the based on what we discussed and what would be the what was also introduced at last July workshop. So what would be the most interesting radar techniques that could be used? For example, what will provide higher impact technically and commercially? So what would be the main requirements from an operator point of view, from the space agency or from an end user of the radar data? What would be that you really want? You want to be able to detect or information about as many targets as you want, or you want to have reliability or association between what you detect with what you have seen before. So what are the KPIs that as that a radar developer should be looking at? Does anyone want to? Yeah.
I think the performance indicators are quite significant. I think based on what Shawn said earlier, and my limited experience of what operators want, I suppose it depends on the customer of the time. So the SSA providers will probably want a different type of information, insofar as doing the big picture compared to the satellite operators themselves wanting some bespoke information for the, I mean, they're only interested in their object against the rest of the catalog. So in some ways, I suppose one could say that, you know, the information they want is their object against anything within their orbital plane.
Mm-hmm. Yes. So probably there is room for different systems with different performance levels that can answer. So basically for different products that can be provided for different customers, basically. So for that type of product, for example, a passive radar might be a cheap solution that could provide a product reliable enough to tell a satellite operator if something is in their orbit plane or not,
as long as it's active.
Yeah.
But and that's the thing, you know, certain systems have their own pitfalls. So in my view, personally, I believe that you know, as wide a selection of tools as possible are important, because they can add different bits of information to just bring down that lack of accuracy or extra accuracy or whatever else. Because radars have limitations. Optical obviously have limitations, one of those being the weather. It's interesting the work we've been doing with Loki and the fact that you know, we're fully au fait on what the limitations are of an optical system, particularly in the northeast of England. But then dealing with some of the authorities when they want data from that system in comparison to data from a radar. And just getting through sometimes that lack of understanding and lack of knowledge that, you know, we're going to operate it differently. We can't do specific tracking because we are looking out, you know, it's a surveillance rather than necessarily a tracking system, etc. So one of the key elements, I suppose, is also educating the customers about what they're asking for and then where best to go to get that information.
Yes. Yeah, it's good to mention that this thing between the optical and the radar sensors, because they both have pitfalls, of course. But something that is also quite relevant is the fusion of the information of the two. So, for example, you know, we've seen Cassandra framework. Cassandra framework can be, for example, an example of an instrument that can be used to fuse the information derived from the type of sensors. That's fusing quite at the later stage the information, but other approaches to the fusion of the information of the sensors can probably be investigated, and this is probably a big research question. So what can we do if we have a radar sensor and direct optical sensor collocated and we try to fuse the information there? Or what happens if we have a distributed heterogeneous system and how do we integrate those information? Because I think these are quite relevant, quite relevant questions that will need to be answered in the future. I think there is a NATO initiative looking into it. I don't know if anyone here is involved in that. There's a NATO initiative looking at fusion of electro-optical and RF sensors for SSA, which is something that's probably worth to keep an eye on, because I believe that there might be a research task group being set up soon. I don't know, is anybody here part of that initiative? No? Okay. If anyone is interested, I can probably give more information, because I'm on it, or at least I'm in the emails. Good. Is there anybody else who wants to contribute?
I think they're all getting coffees at the moment, Carmen. I think if you want to get yourself a drink and everything else, thank you very much for steering the last section, and then we'll flow into the optical side. And I think, are you presenting on that as well, aren't you?
Max is.
Oh, Max is presenting on that, is he? Okay, brilliant. Okay, but that's good. But Max, Carmen, team of Strathclyde, thank you very much. Some great presentations. Did you send them through? If not, could you send them through? So if you're happy for them to go on the GNOSIS website, that'd be absolutely brilliant.
Yes. Yes.
Thank you very much. Okay, everybody. Yeah, welcome back to the second part of this afternoon. Having talked about radar and had some great presentations from the team at Strathclyde, it's now time to swing our attention south of the border, closer to home for me, and that's a team from Durham. I'm going to introduce some ideas on optical tracking. I saw James on there earlier. James, you're ready to roll?
Yeah, hello, I'm here. I can share my screen and we'll get going.
Excellent. Thank you very much.
Okay, well, yes, thank you for the invite to talk about optical tracking capabilities for SST. My name is James Osborne. I'm also hosting this session is Nazim Ali Barmal. We're both from the Centre for Advanced Instrumentation at Durham University. I think it's probably worth a quick disclaimer at the beginning of this. Both Ali and I'm sure Ali won't mind me saying this, are from the astronomical instrumentation background. Excuse me. So we work, or historically we worked more with telescopes looking at stars rather than satellites. There's obviously some overlap. And personally, we're more into adaptive optics, so correcting for the optical effects of the Earth's atmosphere, which gives us high precision astronomical instrumentation measurements, for example, astronomical measurements. And it's that crossover then between the astronomy side and the SST side that got us interested in this. And for the last year or so, we've been getting more into it. So I'm sure there are other people here who are certainly more qualified to do something like this than we are, but we'll give it a shot anyway. So the outline for the next hour really is a brief introduction and state of the field in optical tracking, which I'll do, or try to do, I should say, with the previous disclaimer in mind. And then Ali will talk briefly on the astronomy-inspired active optical illumination. And I'll talk a little bit more about satellite mitigation for astronomy, but also how that could be used for SST as well. And then Max is back to talk about hyperspectral imaging for space objects again. But the whole point of this, right, this is meant to be furthering what we did in the last workshop. So, okay, it's great to have these talks which sort of provoke discussions, but it's really the discussion point that we want to try and make sure we've got time for and try and do. It's difficult, I know, when we're online like this. We've got 45 people online trying to do a discussion, but we'll be back in the same room one day, I'm sure. Okay, so introduction and state of the field in optical tracking. So really it starts with what's the goal then? What do we want to achieve from this session? And the main outcomes of this particular event are to initiate discussions, right? To try and build collaborations, not just with us or with the speakers, but amongst yourselves as well. If ideas come up that you want to work on, you can build on that. So there's 3 presentations to kind of provoke ideas and provoke discussion, but it's sort of beyond that we really want to do. So we're going to try and explore sort of the current capabilities, discuss what the gaps are and how we can push that forward. So sort of from passive side, we're talking about imaging, right? Reflective light imaging. And then the active side as well, using lasers, which is something we do a lot in astronomy. Laser guide stars, for example. They're also already used for SST, obviously, with SLR systems, but maybe we can push that a bit further. And start planning for future workshops and networking events. Obviously, we want to be in person at some point, right? But we'll see how that goes. So the goal really is to reach out between industrial and academic partners, build those bridges between us, to build some significant collaborations. So I know there's some funding available that Din's mentioned at the beginning. If we could use that to really start to build some mass between us that can move forwards and do something useful in the UK, that's even better, right? On the funding, so I don't know if, I don't think Din specifically mentioned it, but the kind of thing we're looking for with the GNOSIS funding in particular is sort of a 7K level for scoping projects and a 30K level for proof of concept. And I think there's also funding for 50% of PhD students as well, which might be useful. So it's not an enormous amount of funding, but it is useful to get something off the ground to do some testing, for example. Okay, so optical capabilities for SST. So this is my opinion, but definitely not an expert in the field, but sort of things that sort of caught my eye and things that are interesting and maybe could be pushed further potentially. So there's a few established techniques that a lot of commercial operators are doing. Geo observations, so imaging of geo is fairly common. Exoanalytics is an example of that. LEO observations are becoming more common. You know, high precision orbital parameters, right, for known objects, okay, particularly for large objects, because they're the objects which have got the potential to cause the most damage to the environment, the space environment. But we also want to push to smaller objects as well to try and understand the number of items up there. We don't really know how many small objects are in space. We don't know how quickly they decay, and all this gives us information about the sustainability of space, right? By which I mean, how many satellites can we actually put up there to exploit without them crashing into each other. We want to start looking at cooperative and non-cooperative objects, right? We want to discover new objects. So it's not just looking for things that we already know roughly where they are and trying to get better, higher precision orbits, but finding new things and trying to characterize the dynamics and the state of the object, okay, its orientation, whether it's tumbling out of control, whatever. And we want to move to all planes, right? LEO, GEO, cislunar, the whole regime. And we want to push to 24/7 operation, because that scales everything. It gives us, instead of losing 50% of time, we can run these systems 100% of the time, so we get more information. And also, I think has already come up a couple of times, perhaps, we need a better database that conserves precision with error estimates as well. So the TLEs aren't really fit for purpose. Okay. So as a bit of a brainstorming that Ali and I went through, we came up with some ideas for potential and non-traditional techniques. This is by no means exhaustive. So we can add to this with your input, obviously. And we've basically split it down to 3 categories. One is technologies, new technologies that can push forwards our current capabilities. The other is data algorithms, using the data from the technology, obviously, to try and extract more information. And then the other set, which I wasn't really sure what to call it, I've gone for applications. There's more things about, you know, how it can be used. What are we trying to do? So if we just go through these really quickly, you know, for technologies, we've got things like laser illumination for characterizing and imaging. AO for laser ranging is something that's starting to happen, including daytime. So one idea actually, which was provoked by Shawn's discussion at the beginning, if you've got a precompensator laser rangers, which means your laser ranging spot is much smaller than it would normally be, which means you have a higher return flux, so you can find smaller objects, right? If you know that you've got a debris cluster coming across, maybe you could scan across it and you can count objects then, because you'll count the flashes that come back. Maybe that's just one way of getting more information out from potentially existing systems. Passive targeted imaging, including the daytime, is something we've heard about in the last workshop. Wide field full sky imaging is sort of around the low-key idea that GNOSIS is working on, to try and get information at scale, right? To see lots of objects at the same time. Hyperspectral imaging, I think Max will talk about later. MKIDs and new types of detectors were spoken about in the last workshop as well. For the algorithm side, then obviously machine learning, we've got data, right? It's very noisy data. There's obviously information in there. How can we extract more information from that? Machine learning is probably a good way of at least thinking about it. It's not it's not a golden bullet. It'll need careful development, but there's potential there. Data fusion has been mentioned already, so optical and non-optical together. Light curve characterization was discussed at the last workshop, so trying to find information on the state of the object based on its reflected light curves is an interesting one. And then modern data formats again, okay. For the applications, obviously we want to go LEO to cislunar right through the full orbital planes. Space-based sensors are another direction it could go in. Daytime operation 24/7 we've spoken about. Pose estimations, this is about characterization and orientation of objects. and moving towards enhanced tasking and cooperation, which I think Shawn also mentioned at the beginning. So on these lists, the ones in italics are the things which were discussed at the last workshop, and the ones that are underlined were discussed at AMOS. So there's obviously some interest there. The colors are just to differentiate them, but this is sort of our list, our going in point, if you like. So if there are any things we want to add to this or take off because maybe it's just obvious, I don't know, then we can do that as well. But this could be a starting point for our discussions and collaboration building. Okay, so that's the introduction. Are there any quick questions on that? Otherwise, we've got 3 talks that we'll try and get through fairly quickly, and then we've got more time for discussion at the end, which I know is awkward, but we can try. So any immediate reflections on this list to begin with? Yes, Norse. I haven't got a name, but it says Norse.
Oh, I didn't know. It's me.
It
stuck with me.
Okay.
It was just a point actually to pick up on, because you rightly mentioned about TLEs, whether or not they're fit for purpose. And the name has completely skipped me again, but there used to be an academic based out of Dundee University, and I know he's working on a spin-off now instead. I'll dig out his details. It'd be good to bring into the discussion, because he gave a great presentation about 7 years ago in the DSTL Astrodynamic Community of Interest event about the significance of TLEs, insofar as obviously some of the things we use them for, they're not fit for purpose. Because I would argue now that maybe the way that we manage traffic in space is definitely inadequate now. But the fact that there's so many systems are reliant on TLEs, and it would take a long time for that technology to flow over, or very expensive to then change. So there will always be a need for the TLEs. I suppose it just depends on what they're being used for. So back to the bespoke requirements of the end user.
Yeah, that's right. I mean, legacy is an issue for everyone, right? Something which is definitely worth thinking about.
Always, particularly actually the people we deal with at the moment, which is defense as well.
Right.
Because we are actually completely entrenched in legacy at the moment.
Yeah, not an easy thing to deal with. Okay. Anything else to discuss? Otherwise, let's move on then. So Ali is going to present some astronomy inspired active illumination. Ali, do you want me to just continue sharing? You tell me when to advance the slides?
Yes, please, James.
Okay.
Right. Hi, everybody. So I think James has given the basic introduction of who we are and what our background is, and that kind of made me gave me the idea for the title for this talk. And so if you go on to the next slide, please. And so my interest in SST will become apparent within a few slides, but if I sort of pull back a little bit and sort of talk about something I covered in the workshop, but where and why I think lasers are important for this particular community. And so, of course, lasers cover many bandwidths, many frequencies, but really I'm talking about optical and infrared. And in these particular wave bands, where the atmosphere, of course, is particularly transparent, they're the alternative illumination source to the sun. I know that there are interesting papers concerning the use of Earthshine. So this is the reflected light from the atmosphere and the surface of the Earth, in fact, which then illuminate objects and then can be used for observation. But here I'm talking about situations where you can consider the SNR to always be high, or you can arrange for it to be high. Okay, so here a laser has a very high brightness temperature, but a relatively low radiance. So the simple illustrations on the right show one of our lasers from the 4-meter William Herschel telescope in La Palma. It's very easy to see, but then you can see the moon during the day very clearly. The sun has incredibly high radiance. So the key point is that lasers have an incredibly high spectral radiance. Now, if you combine that with the fact that using a laser gives us control over the illumination and polarization state, so at this point, we're talking a situation that's somewhat similar to radar. This immediately brings in two particular applications for SSA and SST, which is precision in characterization. So this is really about learning what is the state of your object. Now, by state, I have a very broad set of criteria in mind. It can be the dynamics of the object, so the orientation. It can be its material states. There are examples of rocket bodies in orbits suggesting deterioration, and this has been allegedly monitored from the ground. And the second area really is 24x7 operations. So whereas passively illuminated satellites in the optical become very difficult to see during the daytime, this should be substantially easier because of the spectral radiance characteristics of a laser. Now, I think since we're following the radar session, I should point out that lasers are, as a consequence of some of the information on this slide, unable to compete in terms of wide area. And if you ignore some very speculative but very interesting quantum concepts, are probably unlikely within the next 10 years to be able to view through clouds or other substantial obscuration. So when I say 24/7, I really mean clear skies. So I'd be considering astronomical observatories or other places with relatively few clouds. Okay, next slide, please. Okay, so with that in mind, where and how have lasers been used in astronomy? And probably the major usage has been to generate laser guide stars. Now, these are basically compact beacons within the atmosphere that produce very high spatial coherence. And so they mimic a real star, and so they can in turn be used to monitor the turbulence between the star and the telescope. You can use them in a bistatic configuration, as is increasingly common. And so these systems can be separated, but really in the end, it's this beacon that's sort of interest. And powers have been moderately high, 10, 20 watts, going up to 50 watts. But nonetheless, there are fundamental issues that were discussed in research going back, which have somewhat stopped in the past 10 years. But going back 20 years, certainly, is a very active area of research. And some of them centered around how to rethink this concept of a laser for astronomy. But one particular area, which I'm going to talk about in a moment, is you can see in the image on the right, you have the laser guide star, but behind it or below it is the plume. So this is the backscatter of the light from the molecular part of the atmosphere. And in fact, this backscatter is distorted. I mean, this is a long exposure image, but short exposure images which show that the illumination from the backscatter is not constant, and that's caused by the diffraction of the aberrations in the atmosphere. So the idea was, why don't you use this free signal, this alternative signal, to estimate the aberrations instead? Next slide, please. Now there should be an image here. Okay, there's the image. I didn't realize I'd copied an animation. So what happened was that in 2018, we were introduced to a Australian firm who carry out SSA. And here, this is their image of their facility in Canberra, in Australia. And the real aspects of interest for this talk are the big dome on the left, which contains a 2-meter class telescope, which emits pulses of up to 800 watts. So it's a kilowatt class laser. And so this is transmission. And there is a small 1-meter class telescope, which is marked A2 on the right-hand side. And this we intend to use as a receiver telescope for those for that backscattering that you saw in the previous image. And the idea was that this their DLR, their 2-meter kilowatt class laser, which does laser ranging to uncooperative targets due to the high beam power. And by measuring the backscatter using the smaller A2 telescope, we'd be able to infer the distortions, feed them back to an adaptive mirror within the DLR, and then do pre-correction. So the beam that traveled out into space would be less distorted, well, less diffracted, and so that you get a higher return flux. Unfortunately, application and development of this was considerably stymied by COVID. So really, we're still in a discussion phase with the EOS as to where we're going to go ahead and their priorities. But the basic concept fell into this category. Next slide, please. So there's one important fact that this wombat technique, as it's been rebranded, does not solve, which is the beam wander. And so the atmosphere is an enormous problem for propagating a laser, any optical radiation, because it's significantly distorted, both in final position as it exits the atmosphere, the direction it's going in, and as I've previously alluded to, the diffraction, so how much it's spreading out, the consistency of the illumination. And the two plots on the right basically show in green the theoretical estimate of how the beam, what the beam intensity is on a target as it travels out through the atmosphere, and in blue is a simulation where above there has been no correction for the beam wander, and below there has been. And so the important thing here is that beam wander gets you some way towards removing the effects of the atmosphere. It doesn't do everything, but it does quite a lot, and it might bring you into the region where you have a considerable amount of confidence in how much flux is reaching a target, and also that you can reach a target. So this is work that I developed and presented a poster at AMOS this year. Next slide, please. So if we can correct for beam wander, which is, if you like, the counterpart to wombat, we would be able to increase the illumination precision. Wombat increases the illumination accuracy. Some work to do is to understand if the accuracy is how the accuracy is affected. But previous work showed that with a 1 meter aperture and a 200-watt laser, you can receive 100 photons per millisecond from a 10 centimeter object at 550 kilometers. So this suggests that you will be able to operate with 10 key equipment at 24 × 7 operation with greater confidence at night, because you can use stars to correct for the beam wander. So potential research directions to discuss are really for me, but I'm more than happy to hear from the community what their priorities are and also what their other interests are. So polarization retention. So here what I'm really saying is, when you have this uneven flux that's launched onto an object, and this unevenness, this inhomogeneity is changing all the time because the atmosphere is changing all the time. How does this affect your polarization? Do you get a useful signal back from a laser or not? The second point, I saw some interesting work from a previous AMOS, which suggested that using 2 angles allows you to get a good estimate of the BRDF into one of 5 important categories, which falls into a size mass classification system. And so that allows you to then assess for a target of which you're unsure of the consistency, or perhaps what seriousness it would have in terms of an impact. And the final point that I would like to start investigating a little bit more is, which is, if you really want to use a laser for pure illumination, you're going to find it difficult to target on an object unless you know exactly where it is. And so how do you go beyond point source illumination? So a laser will be able to find a target and track it, as long as you know where to point it. So maybe this is an application of fusion. research for, where you used several types of sensors to use the best capabilities of each sensor to then give you the data set which contains the most information with the least uncertainty. And I think that's it from me.
Thanks, Ali. Any quick discussion points on that one? Or should we save them all to the end?
I notice Din still has his hand up, or has his hand up, I'm not sure which.
Apologies, it still
Still
just
up.
means I'm paying attention to the presentation, just not to the reactions on the bar at the bottom.
Okay. Well, we'll move on then, and we'll have more time for discussion at the end then.
Oh yes, I did have one more slide, which is just as a quick reminder of the laser work from the workshop, which there were 3 talks, two from me and one from one of our colleagues in India.
Okay, so next, I've got a few thoughts on wide field observations for mitigated satellite interference in astronomy, but also trying to think how that could be used for SST as well. Similar to the way that Norse have gone with Loki, I think. But generally, so the idea, right, is to have some wide field camera staring upwards. You want it to be as close to full sky as possible, so we get to see all these satellites. We'd like to use it in the daytime, obviously daytime and nighttime. Okay, so Kilda is a nice dark sky, but there are ways of getting around our sky, perhaps. This obviously feeds, it's not going to be a super precise, it's never going to be a super precise measurement of where satellites are or how bright they are or anything, but could it be used for tasking and data fusion, all this kind of thing that we spoke about before. You do get to see a lot of objects, so it is at scale. And I imagine it could easily be used for an early warning, perhaps for other more targeted methods. And then for what I'm personally interested in is an early warning for astronomical mitigation as well. So, you know, if we have a telescope looking somewhere in the field, then we'll know when a satellite is going to approach that, and we can either avoid it, shutter it. If we know it's there, then perhaps we can post-process it as well. I know everyone must be aware of this conflict at the moment between astronomers and satellite operators, so we want to try and handle that as best we can. So there's a few challenges, right, with trying to build a system like this, and that's because generally satellites in reflected light are actually rather faint. So we've got a trade-off really for the hardware, even, which is this field of view. We want to go as wide as we can, but we've only got a finite number of pixels. So the wider we go, then the worse the angular resolution gets. Now, maybe that's not necessarily a problem, actually, because the satellites will appear as streaks. And because they're streaks, we can do sub-pixel centroiding and get a more precise value of the position, more precise than the resolution of the pixel size itself. And we could think about using different wavelengths and such as well to get more information out. Perhaps if you measure the light curve of these things in different wavelengths, that gives you some information as well. The image processing is really where the key is. So we need the plate solving in order to model the aberrations, and there will be aberrations on wide field systems. And we need to identify the satellites through their vectors, right? So in astronomy, this is actually easy because all I care about is where it's going. So I only need to plot the vector of the satellite. For SST, we probably want to know exactly where it is. And then you have more challenges with timing and such as well involved. And then light curve analysis as well would be the temporal resolution would be an interesting one. So we don't want the exposure times to be too long as well. And then tie into that data management that I've already discussed. So I know that the Loki is a similar system, but I'm not really familiar with many of the details there, but it's probably something that's worth exploring. On the right, I've got an image actually, which is from AstroSat. So if you're not aware of this, this is it's a Python tool which can project satellite orbital parameters into astronomical fields, right? So astronomers can use it and say, okay, if I'm going to look at Vega at 10 o'clock tonight, and with a field of view of X and an exposure time of Y, then which satellites are going to go through that field? And this is something which we developed in collaboration between Durham and Norse, which is quite a nice little tool to use. So if you want to do things like this, then I'd recommend it. Okay, so for astronomy, as I say, we can use this AstroSat tool in order to predict intercepts, but they're only as good as the underlying TLEs. So The middle plot there is something which we might get for, you know, some random field of view from Durham, and we're looking at a star in the middle, black on white here, just to make it easier. And the red trails would be the projected satellite intercepts, and would have, you know, time of intercept, duration, and an estimated brightness. So obviously that, who knows how accurate that is, right? For some of the more studied objects like Starlink, perhaps it's better, but for other objects, we just don't have a clue. And then the plot on the right there shows the same as the one before, but this time with the telescope pointing and projected intercepts. So if you've got your full sky camera, it gives you this early warning, and it gives you validation of the prediction tool. But it also gives us a database of measured brightnesses, which can be used to improve the models and therefore get a better estimate of how we can use this in astronomy, where we can, you know, avoid shutter or post-process, right? So this is what I'm doing for astronomy, but then the question is this also useful for SST? So here's, well, I don't know if you can see this, right? But the plot on the left there is actually a GIF. It's an animation. So we're running through an hour here. And this is a star field. And there's also satellites whizzing across there. And depending on how good this is encoded across the internet signal, you know, you'll be able to see them or not. I hope you can. But the brightness of the satellites, they have little circles around them, and they're on the same color scales as stars, right? Which is where they are quite faint, right? These things aren't bright. And we see these trails going across the sky. So if we do full sky, as I say, we get SST at scale, which is great because we get to see lots of objects at the same time. The precision is a question mark, right? Because, okay, we can get the precision smaller than a pixel, but how good does it need to be useful? And then what is the actual goal of this? Is it an early warning for more sophisticated methods, or what do we want to use it for? Okay, is the question. The problems involved, right? So, okay, it's great to be in a dark site, but actually you don't see many satellites after twilight because they're in the shadow of the Earth, right? So we don't get that reflective light. So really they need to work with a sky background. They need to work in twilight. The plot on the left there is the number of Starlink satellites visible as a function of sun depression angle on the X, and the apparent magnitude on the right. So the magnitude system is an astronomical way of saying brightness, right? So in this case, the magnitude 10 is very faint, so that's the faint end. The magnitude 3 is very bright, so that's the bright end. So you see that we have the most of the Starlink satellites we expect to be between 8 or 9, with a few going down brighter, but really not that much fainter. But as we go, you know, when the sun is maybe 20 degrees below the horizon, which is the end of astronomical twilight, we start to see fewer and fewer satellites. There's a really strong drop off in the number of satellites that are visible to us because they're in the shadow of the Earth. And this is where things like pixel size and exposure time become important, because we want to see these objects, but they're quite faint, right? So really the question comes down to how faint can they be and still be seen. So I've got some mock data on the top right there, where there is a satellite trail through some random Poisson noise from a background with a signal to noise ratio of 1, and I'm making the assumption that I could detect that, right, which I think is probably quite an easy detection to make. And if I do that and I run through some brightness calculations, what it's basically telling me is that when the sun is at 0 degrees, so on the horizon, then we can see satellites down to, you know, magnitude 4.5 to 5, something like that, which is really bright. And there aren't many that bright, right? So you effectively can't see any satellites. And it's only when we get to perhaps 12 degrees below the horizon, so into civil twilight, that sort of area, that we start to see more satellites. So on the plot on the right there, now I've put that dashed line, so all of those satellites just can't be seen, right? So you've got this window, right, between we've got satellites which can't be seen because the sky is too bright, and then the ones that can't be seen because they're in the shadow of the Earth. So the big question really is, how deep does this need to go? How faint do we need to be able to see these satellites in the reflected light? And using a full sky camera with large pixels and some finite exposure time, remember that the exposure time we're talking about here really is the time for the satellite to cross a pixel, to cross the field of view of the pixel, which could be milliseconds. It's quick. So we don't have the opportunity to integrate the signal in a way that you could do with a larger telescope that's tracking the object. So we're really limited to how faint it goes. But this is another question really, is how faint does it need to go? And then sort of the next thing that we want to do is we want to push this to daytime as well, because that's one of the things I stated as a goal. But you know, initially you might think that's just a non-starter because the sky is so bright during the day. But actually, there's some things on our side, right? We know what we're looking for, which is one thing. You know, because the exposure time is longer than the crossing time of the satellite, we get these satellite trails, and they're not point sources, right? So they look different to the noise. So we can use certain statistical techniques to try and extract more information, which is what we do in astronomy all the time. Astronomy is all about trying to extract information from noisy signals. So we've got these priors, right? We know the shape, we know a rough location as well from the TLE data, and we can do filtering. So we can filter for wavelength, for example. You know, reflected light is going to be reflecting the solar spectrum, whereas during the day, definitely the sky is very blue. So there's something we can do there. And the interesting thing here as well is that satellites are as bright during the day as they are during twilight at night, and then they get fainter, right, as we go further into night, as they start falling into shadow of the Earth, with the low orbits going to shadow of the Earth first, and then going to higher orbits. So this is all I really want to say, really. So I've got this idea for doing this for satellite mitigation for astronomy, and I'm trying to explore what that means for SST. So if anyone wants to talk about that, I know that obviously NORSE have the Loki system, but LumiSpace are also interested in something along these lines as well. So getting everyone together, I'd be very interested to see how that goes. And that's my discussion on the wide field tracking. So again, any very quick comments specifically on that, or shall we move on? I can't see any immediate hands up. So that's good. So if I stop showing this, Max, are you there? I think you're up next to show your hyperspectral work.
Yeah. Okay.
Excellent.
All right. Let me share again. Okay, so this is going to be a very short presentation because it's a project that we just started, supported by the UK Space Agency. So I just want to tell you something about the project and give you an idea of some of the initial results that we have from our simulations, and then open the floor for discussion, and if you have any comment or idea. So the work is in collaboration with the Department of Electrical and Electronic Engineering, in particular the Hyperspectral Imaging Center, and the Fraunhofer Center for Applied Photonics. So the idea that I had some time ago was to use the same concept of light curve analysis, but rather than doing it just in the visible spectrum or anyway with the light that is normally received, the idea is to look at individual frequencies and look at the time variation of the intensity per frequency, and possibly extend the range of frequencies that we can analyze when we observe an object in space. So what we started doing is to, first of all, model very simple objects that are tumbling in space. You see here a very simple simulation of a cube. And each face of the cube is covered with a different material. And then we simulated what happens to the light coming from the sun when it bounces against each one of the faces and is received by a hyperspectral imager. So the first model that we implemented assumes that the sensor is in space, so there's no atmosphere, and we assume that the object that we are observing is fairly far away, to the point that effectively we don't see the shape, we only see one pixel, and we want to extract as much information as possible for that single pixel. And the idea is that depending on which phase is, or on which phase the light is bouncing, then the hyperspectral imager will receive a different signature, a different set of frequencies. And so if we are able to actually receive this light and decompose the light that comes from the object, then what we can do is to get the abundance of materials that are reflecting, say, that light. And so what you see here is, again, the simulation of the object. The object is orbiting in LEO, then there is the sensor also in LEO. And here on the left, you see the kind of signal that is received. And then after filtering, then depending on which phase is towards the camera, we can see the relative abundance of material that is reflecting that light. And we can see the same type of simulation also. In this case, you have here the time axis and the light that is decomposed. And for each one of the materials, you see when the filter is telling us that there is mainly that material that is reflecting the light. And this is quite useful because it gives us additional information on the type of object, but also on the attitude motion, because we can now identify different objects on the surface pointing in different directions. And if the object is not just tumbling, but is performing specific maneuvers, then after a while we can understand which kind of maneuvers are associated to which kind of surface. And it's quite interesting that if you look at this peak here, that corresponds to glass. So we can also try to identify possible different objects on the same surface. And we did the same simulation also adding noise to the signal. And we are trying now to model the same process, but assuming that the sensor is not in space, that the sensor is on ground. And we have heard already a lot of the difficulties that are connected to optical measurements from ground. The first thing that we are modeling is simply the kind of noise and attenuation that the atmosphere can add to the signal, and see which kind of sensor, or better, which kind of optics we need on ground connected to this sensor to actually be able to detect something. And as I said, this is the start of the project. The next phase will be to run some experiments, first in a lab, and then try to have some real images. So I cannot really say more than this. This is just the beginning, but happy to receive questions or comments.
Okay, thank you. Any quick direct questions for Max? No, I can't see any hands come up. Okay, thanks for that. So we've got a bit of time left then. We still have 15 minutes or so to form some sort of discussion and ideas, groups, networks, whatever we want to do. I know this is really hard with 37 people, so I don't really know how it's going to work, but does anyone want to react on what we're doing in sort of the optical regime and how we can push this forwards or build on what's been presented or elsewhere even? Does anyone want to kick us off? Okay, we've got a few hands up. David Gooding, I think, is first on the list.
Yeah, hi, James. A question for Max, really, on the hyperspectral stuff. Interested to understand how we think a system like this might cope with an unknown object, with unknown materials. And also what scale of system, has he considered a particular size system from the ground, and how might that look?
So the first filter that we implemented had an assumption on the type of materials. The second filter doesn't have an assumption on the type of materials. Although when we then need to, well, the next phase that I didn't present, I will present maybe next time. When we try to understand effectively what is on the surface, we need to, of course, make some assumptions on the materials. If it's something that is not in the list of the ones that we assume a satellite is made of, at the moment we can simply say that is an unknown signature. So it's not a frequency that is in the list that we have. In terms of size, that's a good question, because it's something that we are trying to figure out in terms of what we need on ground. And it depends a lot on the next set of simulations once we have the atmospheric model connected to the rest.
Sure, thank you.
Stuart, do you want to go next?
Thanks, James. It was just a comment on the point that you made about daytime observations. Back in the day when it was a thing to observe iridium flares, I've had the opportunity to do daytime iridium flare observation up in Edinburgh at the observatory there. And obviously that observation is based on the nature of a particular target that has a reflective surface and some knowledge of the time at which it would actually glint. But I wonder whether for some subset of the targets that we have are interested in, if we have that sort of background knowledge like we did for the Iridium satellites, whether that might help us to actually make observations in the data.
Yeah, I think that's exactly right. I think that's one thing that we do have going for us potentially, is this prior knowledge of the problem, right? So, you know, if you know what kind of thing you're looking at and when it's going to be, then you can try and identify that in the data, and that's always going to help. So I think there are things to explore, right? I can't say whether any of this would work or not, but there's potential, is what we'll say. Okay, Ali.
Hi, everybody. I just wanted to go back to our first speaker who raised some interesting points regarding the ASAT test and some of the capabilities that are potentially missing, especially for the UK. So one particular point was in a very crowded field where it is related to the problem of how do you detect very small objects. So a very crowded field is inevitably made of very small objects. So I'm kind of interested to hear how people think this particular problem should be approached. So of course we're talking about objects that you can't shield from, but also are difficult to see via conventional means, or impossible to see via conventional means. So my understanding is that this size limit is about 10 centimeters. You hear claims of much smaller sizes down to millimeters from commercial operators. But regardless, is this something where it's needed both optical and radar? Is a data fusion approach needed to be able to find targets and then characterize them more precisely using a different wavelength, or are there missing facilities? I'm interested to hear what people have to say on this topic.
Yeah, that is an interesting one, actually, especially with the crowded field idea, which is something I hadn't really thought of before. But you could imagine something where you have like a laser light sheet, whether it's scanning or whatever, where you get the counts back would work, because you know roughly where to look. You don't need to know exactly where each bit of debris is, but because it's this crowded field, then you know roughly their trajectory. and you could intercept that with a laser, right, to count the return. Now you wouldn't know exactly where it is still because of this tip tilt problem that you spoke about, but you'd be able to count it at least.
So I'll put my hand down. I'll just point out that just very quickly that astronomers have been use techniques whereby the timescale of change is used to estimate the scale of objects, and so maybe this is something as well that's relevant to this particular problem, like how fast the signal changes.
Okay, Dins, do you want to say something?
Yeah, it's some very good points about the size of the objects, and I must admit the community, and I'll say more of the space tracking / military space community get quite hung up on it at the moment. You know, what we know factually is that there are, I haven't looked at the catalogue in recent days, but it's 24,000 objects in the catalogue that are being tracked, and there's potential 4,000 plus that are still being tracked but haven't been added to the catalogue because they're still being, you know, so they're still doing the diagnosis of where they've come from, what they're connected to, etc. And then everything else above that is all modelled. So you know, I'm not decrying the accuracy of the models, but we don't know for a fact exactly how many pieces there are. I mean, ESA actually estimate there's 10,000 more trackable pieces than are actually in the catalogue, according to their modelling. But you know, there is no factual evidence of that unless we actually start doing it. And the problem we have, I believe, is that we have too many disparate information sources and too few factual information sources, and it's all out of sight and out of mind. So therefore, why does it bother people on the ground? So finding a way to actually track down those sizes. I mean, the 10 centimeter piece was the filter that the military said this is the size we can see 10 centimeters and above for putting information in the catalogue, and it was tested 3 years ago now by Spacebee, 4 objects that were launched without a license, and that were picked up by the system that were, you know, the FAA or FCC had refused a launch license because they said they were too small to be tracked, and the second they were launched, they were tracked. So then the space surveillance community had the problem of saying, well, do we say we can see them because we told people we can't track to that size? Are we giving away too many secrets? And I think one of the problems is because of the fact that most of the information to do with space objects is held behind the military firewall. There's too many suppositions and too many myths, etc. And the sooner we democratize that data and actually show the fact that there is more out there than they need to worry about, or they should worry about the more, then we need to do it. So tracking smaller objects is far more expensive, so therefore it's avoided. If you don't have enough systems to track it, then how do you corroborate that evidence as being valid, and how do you make sure you're getting accurate evidence? Because one radar that can see objects down to the size of 2 centimeters is not enough to verify the accuracy of that information and project its orbital path and make it verifiable information for conjunction analysis. So yeah, I think there's lots of questions I'm just throwing at you at the moment, James. I apologize for that, but the problem we have is for day-to-day operations, what do we need? And I suppose that hasn't necessarily been identified. For safety of flight, what do we need? But in the meantime, a lot of companies are going to run around saying the sky's falling in and we're heading towards a space debris apocalypse. How do we get the balance between the two?
Yeah, thanks, Dins. Yeah, there's a lot to react on there, isn't there? So a model is only as good as its input, right? As its data. That's certainly true. So where this data comes from is yeah, a really big point that we need to think about. I love the idea of democratizing data. I think that's what we should be doing, especially as my position in a university even is probably one step even further than you would be in an industrial situation, where it's all about making it public and open as possible, which is what I would like to do. But yeah, it's obvious there's still a lot to do. I also like this idea of, you know, it's okay for someone to have this great idea to try and probe down to smaller and smaller scales. You know, we were looking at adaptive optics for satellite laser ranging, for example. And one of the things that we said is, you know, if the wind is in the right direction, we can probably scale it down to maybe 5 centimeters. But like you say, if you've got one system doing that, is that useful? I don't know. I don't know.
It's certainly the accuracy we have within the catalog from the US at the moment is down to the fact that they have a network, and even the limitations of the EU Space Surveillance and Tracking Program. If you look at the map of their assets, most of them are in the geographical location of Europe. Therefore, although it's a fairly large footprint, it's not a global footprint, whereas the US system has a global footprint, albeit with its allies. And for a long time, we're missing information on objects in the southern hemisphere because there were no assets tracking in the southern hemisphere. Now we have a C-band radar in Australia. They have a telescope, the SST in Australia, but they are both feeding the US system. And unfortunately, even for the UK, the National Space Strategy basically was not, in my view, wasn't really much of a strategy. It was more underpinning the defense budget, and we're waiting for the defense space strategy. Well, to be honest, it was written in the National Space Strategy. We're still not looking at the needs of civil space as much as we should be doing. But that's another rant for another forum, I think.
Yes. Okay. And any more discussions of this? I mean, at some point we should try and make an action for a next step. People are more than able to connect amongst yourselves. If you want to put something in the chat, we can react on that. Sorry, Max, I've noticed you've just raised your hand.
Yeah, mine is more a question for expert operations, and so we talk about the size, but what is the minimum size that is required to be tracked individually? So what is the minimum size of fragment that needs to be tracked individually to perform collision avoidance maneuver, for example?
The threshold that's quite often cited is objects around 1 centimeter in low Earth orbit, in particular, carry enough kinetic energy to make a mess of your satellite. So I think there is an aspiration to try and reduce the threshold from 10 centimeters down to about 1 centimeter. So we need an order of magnitude improvement. There is a debate about, if you get unlucky and get hit by a ½ centimeter size piece in the wrong place, whether that could also disable your satellite. Maybe that's true, but the threshold that seems to get talked about most often is moving it down to 1 centimeter.
But one could argue, why do we need to go down to that size right now? Because what evidence do we have of 1 centimeter objects actually causing a problem with orbital traffic? At the moment, in fact, it's satellite size objects that are causing the problem, and we don't necessarily have accurate enough information on that. But I fully agree with what Stuart's saying, that it could ruin your day. We just don't have that much evidence to get governments to put the money into it, and we're back to the economics rather than the technology at the end of the day.
Yeah, I mean, we have suspicions that things like MVSat went offline all of a sudden. We think it might have been hit by something small. We don't really know, and we don't know whether that small thing was a man-made object or a natural micrometeorite. So assuming it was hit by something, it might just have had some sort of other onboard failure. Who knows?
Yeah, the fact it was well beyond its lifespan is the expected lifespan does raise the questions, and that makes the interesting point about on-orbit servicing, and the fact that we've just extended a couple of GEO satellites that were close to the end of their orbital employment. And yet some of the major events that have occurred, bad events that have occurred in GEO in recent years, have come from 18-year-old satellites that have gone beyond their orbital time, or their designated operational time. However, we did lose, was it Intelsat 2029 Echo, was it? I think it was, and that was only about 3 years old when it failed. So yeah, interesting times.
It is interesting, wasn't it? I've heard some people suggest that the small stuff is not something we should worry about so much because it's the big things that cause the damage, right? But if you have a small collision which takes out a satellite, which is the size of a bus or something, then that becomes a big thing that's out of control. Which is the issue there.
Yeah. So when a cloud or fragment initially is created, the ambition is to be able to discriminate between objects that are 1 centimeter.
Yes.
And track them individually.
Yes. And if you look at the aspirations of companies like Leo Labs, they talk about trying to get to that sort of level of performance in their material.
That's interesting. Okay.
Okay. Hira, would you like to add something?
Hi, everyone. Yep, sure. I mean, it's really, really great to be involved in the community, and at least seeing the activity and the tangible progress that we're making is quite heartwarming for someone who's been involved in the community as long as I have. I'm definitely not a veteran compared to many of those on the call that we're working with or alongside, but there's an interesting contrast there, that conversation around object size and tracking down to smaller objects. I think is one part of it, but this emphasis on objects that we can clearly and obviously avoid, that's really our focus on the laser ranging side, in terms of reducing the uncertainty or the covariance matrices for conjunction warnings. That at least an initial step in space traffic management, rather than necessarily trying to measure smaller objects, is to simply understand the situation better, because we've got the two sides. We've got the sensing capability, and then we've got the real world action. And I think the real world action is not taking shape anywhere near as quickly. It's good to see some of the evolution of the conversations at the CAA and the UK Space Agency in terms of how this will be seen for future launch licenses. But what we really need to keep in mind with all of this conversation in the context is that it has to have direct impact to the behavior of satellite operators. And that might not necessarily be in complicating the scenario with increasing the number of objects that they potentially have to avoid, but in giving them better information on. That's really the way that I've been looking at the balance with things from this side at Lumi. Yeah, just a kind of general comment there on the balance between the two.
Thanks, Hira. Yeah, that's interesting. So if I understand you're saying that, okay, it's great to find all these smaller and smaller objects, but actually the precision that we know normal satellite-sized objects isn't quite good enough yet. Is that what you're saying?
Yep. That the covariance and some of the limitations that you've highlighted with TLEs and some of the ways that conjunction warnings are being dealt with, both from the SSA community and processing, and from the satellite operator and their incentives or rather disincentives to do anything about the debris problem. That's just an interesting contrast for me.
Mm. Yeah, okay, that's another spin on the conversation, which I quite like. Actually, thanks for that. Any other discussion points, or we can move on? I can't see any hands going up, so maybe 4:33, we're pretty much bang on time, on schedule to move to the next session.
James, Nazimali, thank you very much for your presentations. Max, thank you for the additional hyperspectral piece as well, on top of all the radar stuff as well. That's been absolutely fantastic. And there is very much a need to follow on from this. And James, I'd like to thank you for highlighting the funding opportunities for GNOSIS. I know I was going to cover them at the end as well, and we'll talk about it in the last few minutes, but that's brilliant. It's over to Stuart now, who will be reminders or update us on the GNOSIS challenges that were thrown out there at the conference.
Dins, can you see that full screen, mate?
Yep, it's coming through full screen. Thank you.
Thank you. Okay, so some of you may have seen these slides before, but I just wanted to highlight the fact that we decided to go into a sort of proactive mode with some of these technical challenges. If you go to the GNOSIS website, you'll find that there are funding opportunities that were mentioned earlier, not huge sums of money, but if you're an STFC-led consortium, there are opportunities to either propose things, or in the case of these technical challenges, to actually respond to some particular, sort of questions that we've put out there to see whether people have some ideas that might actually address them. So the timescales are relatively short, and the funding is similar to the, sort of open call, in the sense that we can go up to about 30K. That's one of the sort of STFC funding limitations that we have to work within. And as I say, the lead organisation should be STFC, but you can, as a commercial entity, work with an STFC partner to actually make a proposal. So we came up with 4 challenges so far, and these challenges kind of anticipate the event that we're hoping to run in January via the GNOSIS network. So a couple of the speakers from Strathclyde and from Durham have mentioned the idea of putting sensors into space, and obviously that has a number of advantages. You're not then potentially working through the atmosphere and the clouds in the atmosphere. Potentially also the ranges to the target objects are much shorter, and you can potentially exploit wavelengths that you can't get very readily through the atmosphere. So this first challenge assumes that we might try and put a space-based infrared instrument in orbit around the Earth, with the idea that it might have the sort of success that NASA's WISE spacecraft had in looking at asteroids, in the sense that some of this debris, whilst it might be in the Earth's shadow and not reflecting sunlight, and might be composed of materials that don't reflect radar very well, because it's close to the Earth and the Earth's albedo, and because it will inevitably go into the sun for part of its orbit, it's absolutely definitely going to have an infrared signature that we may be able to pick up more readily than we can from the ground. So there are some suggestions here about the sort of concept development that we might want to do for an infrared instrument, and then extending that thought in the other direction, in the electromagnetic spectrum, to the other side of the optical. If we were interested in getting more information of the sort that was alluded to earlier, so rather than just doing detection, we actually would like to know more about the shape, size, rotation, pose of various objects in space. Would we be able to do that more effectively with an instrument that was working in the ultraviolet? Because if we're working at shorter wavelengths, potentially the resolution for a given sized aperture should be better. So does that make our job of getting the sort of information that we want at the sort of ranges that we want it easier if we actually put a UV instrument in space instead? The third technical challenge comes from Don Polacco at the University of Warwick, and he's interested in the idea of stacking images. Essentially, the idea is to track a sensor across the sky at the expected orbital rates of various objects in Earth orbit. A lot of the things that we want to find are in sun-synchronous orbits, passing roughly north-south over temperate latitudes or south-north. So you can anticipate the likely motion and rates across the sky. And then potentially there's a data processing challenge to actually anticipate the target velocities across the field of view and stack the images appropriately to actually pull out smaller objects by aggregating their light into a particular area of the detection system. And the final challenge sort of rather relates to the things that Darren were talking about earlier. So daytime imaging, but this time in the infrared, can we actually utilize the signatures that I was talking about that all satellites will have in the infrared, and all debris will have in the infrared, to actually detect them and exploit various characteristics that we think they're likely to have. The inclusion of polarization filters, for example, is mentioned on this slide. So these are the challenges that we've put out in front of the community, and if people are interested, we would be very interested to receive proposals. It's a pretty straightforward process to apply. If you go to the GNOSIS website and hit the funding tab, there's a very simple expression of interest form, which is pretty much tell us who you are and what your email address is. And then there's the opportunity to submit your proposal, and it doesn't have to be long. The sort of template assumes a certain number of words, and that number of words is not huge because we're not expecting you to write a master's thesis in order to qualify for the sort of levels of funding that we're putting on the table. So that's the process if you are interested in trying to get your hands on some of this money to take some of these concepts, ideas forward. If I can just finish with a quick invitation, the next GNOSIS event will be around space-based surveillance of space. So obviously some of these concepts that I've just been talking about are the sort of things that we're hoping to get into a bit more detail on. It's due to be on Thursday, January the 20th, 2021. Sorry, that should say 2022. I wasn't thinking when I typed. We're not going back in time, sadly. But anybody who would like to contribute to the agenda for that event, please can they email me, hopefully before Christmas, and I'll be putting the agenda for that event together and circulating details early in the new year. So at that point, I'll stop, and if anybody's got any questions, very happy to take them. Thanks very much.
Thanks, Stuart.
Looks like James has his hand up, if that's not a legacy hand.
No, hi Stuart. Yes, that's interesting. Actually, your number 3 about stacking algorithms and things like that. Actually, I have a master's student working on exactly that right now.
Do you think that you could tie your master's student up possibly with Don Polacco, because Don's the author of that particular challenge, and if your student is doing something that's germane, then potentially there's some supporting funding that could be available to help with their research.
Yeah, I mean, absolutely. Should I talk directly to Don about that then?
I would suggest an email to Don, but then if you are able to get your student to go on to the GNOSIS website and just go through that process that I outlined just now to just register your interest, that would be fantastic.
All right, thank you.
Cheers, James. Do I have to modify my display to see other people's hands?
I'm certainly not seeing any. Is there anybody else with any questions for Stuart before we close out today's Sandpit? So I don't see any other questions at the moment. All I'll do is just quickly reflect on this afternoon's proceedings, because it's been some very good presentations, both on the radar and optical side. The key piece to think about is the fact that we're very keen to spend GNOSIS's money, or should I say STFC's money, at the end of the day, and trying to get projects together to apply for and successfully get those funding streams have been quite problematic over the past couple of years. Unfortunately, GNOSIS was formed just before the pandemic, so there has been numerous problems of actually getting people together. An ideal Sandpit would be in a room brainstorming rather than trying to hold discussions across the internet. But the aim of the network was to fund. I mean, James mentioned it earlier. There was 2 part-funded PhD projects. The first one was awarded fairly early on in the program. There's still one potential, but until the next steering board, I don't know if they'll be advertising and funding the second PhD student. But there was 10 scoping studies over the 4 years of GNOSIS and 4 proof of concept studies, and so far all that's been awarded is 1 proof of concept study, and that's it. And of course the challenges were brought in to hope to spend that money as well, and that too is funding there that's available for everybody to to support or to at least apply for. The application process is online, and it is similar to the challenges, the expression of interest, etc. And it just has been quite problematic. I think one of the very early funding streams or very early proposals was overly commercial, and that's when we discovered about the rules about the funds go via SDFC supported research institutes. Hence the idea is to have as many people involved in this as possible from academia. That's the way forward, and the way we can get commercial space and academic space to work together to be able to support this is ideal. Certainly, James, you and I, and more importantly, Lawrence from our team, need to talk more to see what else we can do and start developing it. I know that early collaboration with you and Lawrence developed the tool to support astronomy and satellites, or satellites were in the astronomic field of view. But there's still time left to spend this money, and it would be great to be able to actually have some success stories through GNOSIS to help the longevity of the project and to drive that collaboration further. So if we are able to scope some studies for either radar projects and or optical or laser ranging, etc., then that would be good. And I welcome the opportunity to discuss this out with the today's program, and to look forward to other future events. Next year there will be another GNOSIS conference, and maybe we'll have something in place in time to support that. I also do understand, James and I have spoken briefly about this, the fundamental problems of small pockets of funding and how much harder sometimes it is to go for them compared to the bigger research projects, and the fact that they're already well and truly established. And if that is the case, then this is the sort of thing that the membership of GNOSIS need to push forward to the steering committee, and so they can re-evaluate the way forward and hopefully have the funds actually channeled in the correct way to support future research. At the end of the day, the SST world, according to DINS, is inadequate for what we need for the future. I would say once Starlink started launching 60 plus objects a time, we soon reached the capacity, or exceeded the capacity, of the US defense to be able to support global space operations. They're trying to do a job. They're doing a very good job with what they've got, but they're obviously not funded to do that. And we've been waiting for the US Department of Commerce to start doing more. And they, again, seem to be hitting the funding brick wall. And so therefore, this role will be remaining in the hands of US defense for the foreseeable future. The more that we can lobby and persuade the UK to get involved in what they lovingly call SDA, space domain awareness, the more that they will then actually channel funds into research to be able to support the long-term sustainability of space, and potentially do more if just to support UK space. And the beauty with that is the fact that with OneWeb now being part owned by UK government, even though it's not such a huge part anymore, they do have a far greater interest. And I know the UK register of objects of interest has gone from 80 to close to 300 now, if I remember rightly, because of the fact that they've been launching so many OneWeb satellites. And so therefore the UK has a far greater responsibility to be a responsible space actor than it ever had before. I think there's very little else I can say. I'm not going to get on my soapbox and talk about that. I think ideally we need to get together, whether it's in larger groups or small groups, and put together some proposals to be able to support the needs of or the funding streams of GNOSIS. Unless anybody has any further questions for me, and please do raise your hands if you do. This just really, I just need to remind everybody to please feedback to GNOSIS your thoughts on the workshops and sandpits that have been held over the past couple of years, and the future programs. And if you have any subjects that you think should be explored in greater depth in the future, then please do feed that into GNOSIS itself. James Blake, that is, correct me if I'm wrong, but I think we'll be sending out a follow-on email with a link to a survey. Is that correct?
Yes, I believe Teresa will have that prepared. So anyone who's on the call, if you just keep an eye out in your emails for any GNOSIS related emails that come through, there'll be a feedback survey, and we'll also distribute the link to this recording for anyone that had to miss certain parts or couldn't take notes when they wanted to, etc.
And to all those presenters that have presented today, thank you very much for your time. Could you send PDFs of your presentations through, and we'll put them onto the website as well for everybody to have access to. And hopefully Shawn's presentation will be there. They've just got to go through a space agency process to be able to put the full presentation, but the recording will be available anyway for people to view. Unless there are any other questions, I'd like to thank everybody for their time, for joining us today. I'd like to thank all our presenters, and Merry Christmas to everybody. I hope you have a great, merry and safe holiday, and see you all next year. Thank you very much for your time.
Thank you. Thank you.
Thank you,
Happy
Jens.
Christmas.
Thanks.